Welcome to Quiet Science Nights, a place where we explore the vast universe through gentle scientific storytelling, combined with soothing sounds to help you relax and drift effortlessly into sleep. Let your mind unwind, and together, let's begin our journey into the deep mysteries of space.
Now, the idea of a star exploding might sound dramatic at first, maybe even a little alarming. But there's something strangely calming about it too, once you take a step back and look at the bigger picture. Because these events, as powerful as they are also part of a rhythm, a slow, patient unfolding that takes millions, sometimes billions of years to reach that final moment. Before we ease into that moment though, let me ask you something simple. Where are you listening from right now? And what time is it in your little corner of the world? Maybe it's late evening, the kind of hour where everything starts to quiet down. Or perhaps it's earlier, and you're just taking a moment for yourself before the day continues. Either way, it's kind of fitting, isn't it? A story about stars ending, told in a moment where things begin to slow, soften and settle. If you find this kind of journey soothing, or just a gentle way to unwind, I'd be quietly grateful if you gave the video a like and maybe subscribed. It helps this calm little corner reach others who might need a slower pace too. Now, let's begin, not with an explosion, but with something much quieter. Imagine, for a moment, a star. Not as a distant point of light in the sky, but as something real, something immense, something steady. It's been there for longer than any human history, longer than most of the structures of our planet. Just quietly existing, glowing, holding itself together. And that's really the key word here, holding. Because a star at its core is a balancing act. Inside it there's an ongoing struggle. Not a violent one, not something chaotic in the way we might picture, but a constant steady push and pull. On one side there's gravity, always trying to pull everything inward, to compress the star, to make it smaller, denser, tighter. On the other side, there's energy, specifically the energy from nuclear fusion, deep in the star's core, pushing outward, holding everything up. For most of a star's life, these two forces are perfectly balanced. It's almost like the star is breathing, in a sense. Not literally, of course, but there's a rhythm to it. Gravity presses in, fusion pushes out, and the result is stability. A steady glow, a quiet presence in the night sky. And this can go on for an incredibly long time. Our own star, the Sun, has been doing this for about 4.6 billion years already, and it's expected to keep going for another 5 billion or so before anything dramatic happens. So when we talk about stars ending their lives, we're not talking about something sudden in the grand scheme of things. We're talking about the final moment in a very long, very patient story. But here's where things begin to shift. Eventually, even the most stable systems run into limits. Inside a star, the fuel that powers fusion, usually hydrogen at first, doesn't last forever. Slowly, over millions and billions of years, that hydrogen gets used up. It fuses into helium, releasing energy in the process. That energy is what keeps the outward pressure going. But as the hydrogen runs low, something subtle begins to change. The balance starts to wobble. At first, it's not dramatic. There's no sudden collapse, no explosion, just a gradual shift. The core begins to contract slightly as the outward pressure weakens. Gravity starts to gain a little more ground. Not all at once, but enough to matter. And when the core contracts, something interesting happens. It heats up. You might expect compression to make things tighter, maybe colder, but in stars, compression actually raises the temperature. It's a bit like squeezing air in a pump. The tighter it gets, the hotter it becomes. So as the core shrinks slightly, it gets hotter. And that heat allows new kinds of fusion to begin. Helium can start fusing into heavier elements. The star adapts in a way, finding new ways to keep that balance going. For a while this works. The star expands, sometimes becoming much larger than it was before. It might turn into what astronomers call a red giant. A phase where the outer layers puff outward, glowing with a softer reddish light. From the outside it can look calm, even beautiful. But inside, things are becoming more complicated. Each stage of fusion produces heavier elements. Hydrogen becomes helium, helium becomes carbon, then oxygen, and so on. With each step, the star is building more complex materials in its core. And here's the important part. Not all fusion gives back the same amount of energy. At some point, the star reaches a stage where the fusion process doesn't provide enough outward pressure to counteract gravity. The balance that held everything steady for so long starts to fail, not abruptly but inevitably. It's a bit like a structure that's been carefully supported for years, slowly losing the beams that hold it up. And once that support weakens enough, gravity doesn't just win a little, it takes over completely. Now, depending on the size of the star, this next part can unfold in very different ways. Smaller stars, like our Sun, will have a gentler ending. They'll shed their outer layers slowly, leaving behind a dense core. But much larger stars, the ones many times the mass of our Sun, follow a different path. And this is where the idea of a supernova begins to come into focus. Because in those massive stars, when the balance finally breaks, it doesn't just lead to a quiet collapse, it leads to something far more dramatic. Picture the core of the star, which has been building heavier and heavier elements over time. Eventually it reaches iron, and iron is different. Unlike earlier fusion stages, fusing iron doesn't release energy, it actually consumes it. So when the core fills with iron, the star loses its ability to generate the outward pressure it needs to hold itself up. Fusion can't save it anymore. Gravity, which has been waiting patiently this entire time, suddenly has nothing holding it back. And in that moment, everything changes. The core begins to collapse, not slowly, not gently, but incredibly fast. Faster than anything we experience on Earth. In a fraction of a second, matter that once filled a vast space is squeezed down to something unimaginably dense. It's almost hard to picture. Imagine something the size of a planet being compressed down to something the size of a city. And that's still an understatement. The particles inside the core are pushed so close together that the normal structure of atoms starts to break down. Electrons are forced into protons, creating neutrons. The core becomes something entirely different. A dense, compact object made mostly of neutrons. But here's the part that makes a supernova what it is. That collapse doesn't just continue inward forever, at least not immediately. At a certain point, the core becomes so dense that it can't compress any further. It reaches a kind of limit, and when the inward collapse suddenly stops, all that falling material crashes into it. And then, something remarkable happens. It rebounds. That inward collapse turns into an outward shock wave, a sudden powerful burst that travels back through the star's outer layers. And this is where the explosion begins. The energy released in that moment is staggering. For a brief time, the star can shine brighter than an entire galaxy. Not because it's getting bigger, but because it's releasing an enormous amount of energy all at once. From far away, it appears as a new point of light in the sky, one that wasn't there before. Ancient astronomers sometimes called them guest stars because they would appear suddenly, stay for a while, and then fade. But what they were really seeing was the final moment of a massive star's life. And interestingly, even though we call it an explosion, it's not like something being blown apart from the inside in a simple sense. It's the result of a collapse, a failure of balance. Gravity finally taking over, followed by a rebound that sends everything outward. It's a process that begins quietly, with a slow loss of fuel, and ends in something incredibly bright. And yet, even in that brightness, there's a kind of order to it. Because everything that gets thrown out into space during that explosion, all those heavier elements created over the star's lifetime, doesn't just disappear. It spreads out, mixing with the surrounding space. Those elements, carbon, oxygen, iron, and many others, go on to become part of new stars, new planets, and eventually in some cases things like us. So in a very real sense, supernovae are not just endings, they're also beginnings. Somewhere out there, long before any dramatic ending or sudden burst of light, there is just a star quietly doing what it has always done, holding itself together, shining steadily, and going about its business in a way that, from a distance, seems almost simple. But when you pause for a moment and really think about it, what even is a star really? Not just a bright dot in the sky, not just something we point at on a clear night and casually admire, but an actual object, something real, with structure, with rules, with processes happening inside it every single second. Because it's easy to forget from here on Earth that a star is not a solid thing. It's not like a rock or a planet. You can't stand on it, you can't touch it. And if you somehow got close enough, you wouldn't find a surface in the way you might expect. Instead, a star is more like a vast sphere of gas, mostly hydrogen, a bit of helium, and trace amounts of other elements, all held together by gravity. And when I say vast, I mean on a scale that's difficult to fully picture. Even our own sun, which is considered an average star, is so large that you could fit over 1 million Earths inside it. And yet, despite being made of gas, it doesn't just drift apart into space. That's because of gravity. Gravity is what pulls all that gas inward, toward the centre. Every bit of matter inside the star is tugging on every other bit, creating this constant inward pressure. If that were the only force at play, the star would simply collapse in on itself. But it doesn't. And the reason it doesn't is where things start to get interesting. Deep inside the core of a star, something is happening that changes everything. The pressure and temperature there are so extreme that atoms don't behave the way they do here on Earth. Under those conditions, hydrogen atoms are pushed so close together that they fuse. They combine to form helium, and in doing so, they release energy. A tremendous amount of energy. This process is called nuclear fusion. It's the same basic idea behind hydrogen bombs, but in a star it's happening in a controlled, continuous way. Not as an explosion, but as a steady reaction that can last for millions or billions of years. And that energy doesn't just sit there, it pushes outward. So now you have two forces at play. Gravity pulling everything inward, and energy from fusion pushing outward. And when these two forces are balanced just right, the star reaches a state called equilibrium. That balance is what allows a star to exist in a stable way. You can think of it like a constant tug of war, where neither side wins. Gravity is always trying to compress the star, while fusion is always trying to expand it. And as long as those two forces stay in sync, the star remains steady, shining quietly. It's not frozen or static. There's movement everywhere inside it. Energy is being generated, particles are colliding, layers are shifting, but from the outside it looks calm. Just a steady point of light. Now, here's something that might seem a little counterintuitive. The size and brightness of a star depend largely on its mass. The more massive a star is, the stronger its gravity, and that stronger gravity compresses the core more tightly, raising the temperature even higher. That increased temperature speeds up fusion, which means more energy is produced. So bigger stars don't just shine brighter, they burn faster, and this leads to an interesting trade-off. A small star can burn its fuel slowly, lasting for billions, even trillions of years, but a massive star, the kind that will eventually go supernova, lives a much shorter life. It burns through its fuel quickly, sometimes in just a few million years. It's a bit like comparing a candle to a bonfire. The candle burns gently, slowly, lasting a long time. The bonfire burns intensely, brightly, but it uses up its fuel much faster. Stars follow a similar pattern, and this is important because it means that not all stars are destined for the same kind of ending. Only the most massive stars, the ones that burn quickly and live intensely, have the conditions needed to eventually collapse and explode as supernovae. Smaller stars like our Sun will take a different path, one that's far less dramatic. But before we get too far into endings again, it's worth staying with the idea of what a star is while it's still stable. Because even during its calm, long-lasting phase, a star is far from simple. Inside it, energy created in the core doesn't immediately reach the surface. It can take thousands, even hundreds of thousands of years for that energy to make its way outward. It moves through layers, bouncing from particle to particle, gradually working its way toward the outer regions, and once it finally reaches the surface, it radiates into space as light and heat. That's the sunlight we feel on Earth, the warmth on your skin on a clear day, the light that lets plants grow, that drives weather patterns, that supports life in ways we often don't even think about. All of that begins in the core of a star, in those tiny fusion reactions happening continuously. It's quite a quiet process in a way. No sudden bursts, no dramatic flashes, just a steady output of energy over immense spans of time. And yet, within that steadiness, the future of the star is already being shaped, because every fusion reaction changes the composition of the core just a little. Hydrogen becomes helium. Helium builds up. Over time, the balance inside the star subtly shifts. It's not something you would notice from the outside, not over short timescales anyway. But over millions or billions of years, those changes add up. The star evolves. And this idea of evolution is key. A star is not a fixed object. It has a life cycle. It forms, it stabilizes, it changes, and eventually it reaches an endpoint. That endpoint depends on how massive it is, how fast it burns its fuel, and how the balance between gravity and fusion shifts over time. But at its core, throughout all these stages, the fundamental nature of a star remains the same. It is a place where gravity and energy are in constant tension. A place where matter is being transformed. A place where the simplest element in the universe, hydrogen, is gradually turned into something more complex. And this transformation doesn't just affect the star itself. Over time, stars become factories for elements. The carbon in your body, the oxygen you breathe, the iron in your blood, all of these elements were formed in stars at some point in the distant past. Which means that when we look at a star, we're not just looking at a distant object. We're looking at a process that, in a very real sense, made everything around us possible. That might sound like a big idea, but it's also a quiet one, because it happens slowly, over timescales so vast that they're hard to fully grasp. There's no urgency to it, no rush, just a steady unfolding. And within that unfolding, there's always that balance, gravity pulling inward, fusion pushing outward, a constant negotiation between collapse and expansion. As long as that negotiation holds, the star continues on, shining steadily, seemingly unchanging. But, as we touched on earlier, that balance doesn't last forever. The fuel changes, the conditions shift, and eventually the forces that once held everything in harmony begin to fall out of sync. It doesn't happen all at once. There's no sudden switch from stability to chaos. Instead, it starts as something subtle, a slight imbalance, a gradual change in the core, the kind of change that, at first, might not seem like much at all. But over time, that small shift grows, setting the stage for everything that follows. If you were to watch a star live its life from beginning to end, not in the way we usually observe the sky, but as if time itself had been gently sped up just enough for you to notice the changes, you might be surprised by how uneventful most of it appears. Not empty, not meaningless, but steady, predictable, almost patient. Because for the vast majority of its existence, a star isn't exploding, collapsing, or doing anything particularly dramatic. It's simply continuing, holding its shape, maintaining its balance, quietly converting one form of matter into another, second after second, year after year, for spans of time so long that even thinking about them requires a bit of mental stretching. And that long, steady stretch, that's where most of a star's story takes place. To understand it, it helps to imagine not the end, not the moment of collapse, but the middle, the longest chapter, the one that defines what a star really is during its lifetime. Once a star forms, after that early stage where clouds of gas come together and gravity pulls everything inward, it settles into what astronomers call the main sequence. You don't need to remember the term, but the idea behind it is simple. This is the stable phase, the part of the star's life where everything is more or less in balance. Inside the core, hydrogen is being fused into helium. That process releases energy, and that energy pushes outward, holding the star up against its own gravity. As long as there is enough hydrogen in the core, and as long as the temperature and pressure remain high enough for fusion to continue, the star stays in this state. And this phase can last a very long time. For smaller stars, it can last trillions of years, far longer than the current age of the universe. For stars like our Sun, it's around 10 billion years, and for the most massive stars, the ones that will eventually go supernova, it's much shorter, maybe a few million to tens of millions of years. Short in cosmic terms, still unimaginably long from a human perspective. But regardless of the exact length, the nature of this phase is similar across stars. There is a kind of quiet consistency to it. Energy is produced in the core, slowly making its way outward. The outer layers glow, radiating that energy into space. The star maintains its size, its brightness, its overall structure, with only subtle changes over time. From a distance, it might seem like nothing is happening at all, but inside, things are always moving. At the core, where fusion is taking place, conditions are extreme. Temperatures can reach millions of degrees. Pressure is immense, and within that environment, hydrogen nuclei, just single protons, are constantly being pushed together. Now, hydrogen atoms don't normally want to fuse. Their positively charged protons repel each other. But in the core of a star, the temperature is so high that particles are moving incredibly fast enough to overcome that repulsion occasionally, and when they do, they fuse. That fusion releases energy, and it also creates helium. So over time, the core of the star slowly changes its composition. At first, it's mostly hydrogen, but gradually, as fusion continues, helium begins to build up. It doesn't happen quickly. It's not something you would notice in any short span of time. But over millions and billions of years, the balance shifts. And this is one of the key ideas to hold on to. A star's life isn't static. Even during its most stable phase, it's evolving. Very slowly, very gradually, but continuously. The amount of hydrogen in the core decreases. The amount of helium increases. The conditions in the core adjust in response. Temperature, pressure, density. All of these factors shift slightly to maintain that balance between gravity and fusion. It's a bit like a long-running system that keeps adjusting itself to stay stable. If one side of the balance changes, the other side responds. If fusion slows slightly because there's less hydrogen, gravity compresses the core a bit more, raising the temperature, which in turn increases the fusion rate again. It's a kind of self-regulating process, and for a long time this works beautifully. The star remains stable, it shines steadily. It goes about its life in a way that, from the outside, seems almost unchanging. But that stability depends on one thing above all else: fuel. As long as there is enough hydrogen in the core, fusion can continue, and as long as fusion continues, the outward pressure can counteract gravity. So the star lives on, and this brings us back to the idea of mass. Because the amount of fuel a star has, and how quickly it uses that fuel, depends on how massive it is. A smaller star has less mass, which means less gravitational pressure in the core. That leads to lower temperatures and a slower rate of fusion. So it burns its fuel slowly, stretching its life out over a very long time. A massive star, on the other hand, has much stronger gravity. That compresses the core more, raising the temperature significantly. Fusion happens much faster, releasing more energy, but also consuming fuel at a much higher rate. So even though a massive star starts with more fuel, it uses that fuel so quickly that its overall lifetime is shorter. It's a bit like having a large tank of fuel connected to an engine that runs extremely fast. You might have more fuel to begin with, but you're burning through it at such a high rate that you don't last as long. And this is why the stars that will eventually go supernova live such relatively short lives. They burn intensely, they shine brightly, and they use up their fuel quickly. Now, during this long phase, the star is also interacting with its surroundings, even if it doesn't seem like it. It emits light, of course, but also particles, stellar winds, streams of charged particles that flow outward from the surface. These winds can shape the space around the star, pushing away nearby gas and dust, influencing the formation of other stars and planetary systems. So even in its quiet phase, a star is not isolated. It's part of a larger environment, part of a system that is constantly changing, even if those changes are slow. And then there's something else to consider. The passage of time, not as we experience it, but as it applies to a star. For us, time feels linear and immediate. Days pass, weeks pass, years pass, and we notice the changes. But for a star, especially one that lives for billions of years, time operates on a completely different scale. What we would consider an incredibly long period might be just a small fraction of a star's life, which means that most of what a star does happens so slowly that, from our perspective, it appears almost frozen. But that doesn't mean nothing is happening. It just means that the processes are stretched out over such vast timescales that they become difficult to perceive. And yet, all of those slow processes are leading somewhere. The gradual build-up of helium in the core, the slow decrease in hydrogen, the subtle adjustments in temperature and pressure. All of these are part of a long progression, a progression that eventually leads to a turning point. At first, that turning point is not obvious. The star continues to shine. From the outside, it still looks stable, but inside the balance is becoming harder to maintain. The core composition is changing, the fuel is being used up, and the system that has been regulating itself for so long begins to approach its limits. It's not a sudden failure. It's more like a slow drift toward instability. The kind of change that, if you could observe it over millions of years, would become clear. But from any shorter perspective, it feels almost invisible. Still, it's there. It becomes clear that the quiet, slow life of a star is not just a backdrop, it's the foundation. Everything that happens later, every collapse, every explosion, every dramatic event, is built on the conditions that develop during this long, steady phase. So before anything changes in a more obvious way, it's worth holding on to that image of a star in its prime, stable, balanced, quietly shining. At some point, without any dramatic signal or sudden announcement, the steady rhythm that has carried a star through most of its life begins to change. Not all at once. Not in a way that would be obvious if you were simply looking up at the sky on a clear night. From a distance, the star still shines. It still holds its shape. It still appears as stable as it has always been. But inside, something is shifting. And it starts with something quite simple. The fuel that has been powering the star for so long is slowly running out. For millions or billions of years, hydrogen in the core has been fusing into helium, releasing energy, and maintaining that delicate balance between gravity pulling inward and energy pushing outward. It has been a reliable process, one that has kept the star steady through nearly all of its life. But hydrogen is not endless. Even in a massive star, even in one that begins its life with an enormous supply, the core gradually becomes depleted. Not empty, not completely gone, but reduced enough that the conditions begin to change. At first, the difference is subtle. The rate of fusion slows slightly. Not enough to cause any immediate instability, but enough to matter. Because that outward pressure from fusion is what holds gravity in check. And when it weakens, even by a small amount, gravity begins to press in a little more firmly. So the core contracts, just slightly. It's not a collapse yet, not anything dramatic, more like a gentle tightening. The kind of shift that would go completely unnoticed if you weren't looking directly at the internal structure of the star. But as the core contracts, something important happens. It heats up. This might seem counterintuitive at first, but in stars, compression leads to higher temperatures. As gravity pulls matter inward, the particles are packed closer together and their interactions become more energetic. So the temperature in the core rises, and that increase in temperature allows a new stage of fusion to begin. Helium, which has been building up as a product of hydrogen fusion, can now start to fuse into heavier elements like carbon and oxygen. This process requires higher temperatures than hydrogen fusion, which is why it doesn't happen until later in the star's life. So, in a way, the star adapts. As hydrogen runs low, it finds a new fuel, and for a while, this restores the balance. Fusion ramps up again, producing energy, pushing outward, counteracting gravity. The star stabilizes once more, though not in quite the same way as before. Because while the core is now fusing helium, the outer layers of the star respond to these internal changes. They expand. The star grows larger, sometimes much larger than it was during its earlier life. Its surface cools slightly, giving it a reddish appearance. This is the phase often referred to as a red giant, though the exact details vary depending on the star's mass. From the outside, it can look almost serene, a large glowing sphere, softer in colour, more diffuse in shape. But inside, the processes are becoming more complex. The core is no longer a simple region where one kind of fusion dominates. Instead, it begins to develop layers, different regions where different types of fusion occur depending on the temperature and pressure. Hydrogen might still be fusing in a shell around the core, while helium fuses deeper inside. As time goes on, even heavier elements can form in the innermost regions. It becomes a kind of layered structure. And with each new layer, with each new stage of fusion, the star moves further away from the simple balance it once had. Because here's the thing, each new type of fusion is less efficient at producing energy. Hydrogen fusion is relatively stable and long-lasting. Helium fusion requires higher temperatures and doesn't last as long. Fusion of heavier elements happens even faster and produces less usable energy in terms of maintaining that outward pressure. So the star finds itself in a situation where it has to work harder to maintain balance. Gravity is always there, constant, unrelenting. But the fusion processes that push outward are becoming less effective at counteracting it. And this is where the balance begins to slip in a more meaningful way. It's no longer a perfect equilibrium. It's more like a system that is constantly adjusting, trying to compensate for changes but gradually losing its ability to do so. The core contracts, heats up, ignites a new fusion process, expands slightly, stabilizes for a while, and then repeats the cycle. Each time, the changes happen more quickly. Each stage is shorter than the one before. If the main sequence phase lasted millions or billions of years, the helium burning phase might last much less. And the stages beyond that, where heavier elements are fused, can be incredibly brief in comparison. In massive stars, the final stages can unfold in a matter of days or even hours. But we're not quite there yet. At this stage, the star is still holding on, still adapting, still managing to keep gravity from completely taking over. And yet, the direction of change is clear. The core is becoming denser. The temperature is rising. The composition is shifting toward heavier elements. And with each of these changes, the ability of fusion to maintain that outward pressure becomes more limited. It's a bit like a system running through its reserves. At first, everything operates smoothly. Then adjustments are needed. Then those adjustments become more frequent, more strained. Eventually, the system reaches a point where the adjustments are no longer enough. But before that final point, there's a period where the star is in a kind of delicate, unstable balance. Not collapsing, not exploding, but no longer truly stable either. And this is where things start to feel different. If you could observe the star closely over long periods, you might notice changes in its brightness, small fluctuations as the internal processes shift. You might detect changes in its outer layers, expansions and contractions that reflect what's happening deep inside. But these are subtle signs, nothing that would immediately suggest what's coming. Because from the outside, the star still exists, still shines, still looks more or less like a star, and that's part of what makes this stage so interesting. The most important changes are happening out of sight, deep in the core where the conditions are becoming more extreme, where the balance that once defined the star is slowly giving way to something else, something less stable, something that can't be maintained indefinitely. And as we continue to follow this process, it becomes clear that the slipping balance is not a sudden event. It's a gradual shift, a long, slow movement toward a point where the star can no longer support itself in the way it once did. A point where gravity, which has always been there, quietly waiting, finally begins to take a more dominant role. And once that happens, the changes that were once slow and subtle begin to accelerate. The core contracts more rapidly, the temperature rises more sharply, the fusion processes struggle to keep up, and the star moves closer to a threshold. A threshold where the balance doesn't just slip a little, it breaks. But before it breaks completely, there are still a few more stages to understand, a few more steps in this long progression. Because the final collapse, the moment that leads to a supernova, is not just the result of a single change. It's the culmination of everything that has been happening up to this point. Every fusion reaction, every shift in the core, every subtle imbalance that gradually built over time, all of it leading toward a moment that, when it arrives, will seem sudden, but in reality has been a long time coming. There's a moment in many slow-moving systems where nothing appears wrong at first glance, and yet, if you knew where to look, you would begin to notice small inconsistencies. Not dramatic failures, not anything that demands immediate attention, but subtle hints that the steady state that once defined everything is becoming harder to maintain. A star approaching collapse enters a phase like that. From far away, it still looks like a star. It shines, it holds its general shape, and it continues to radiate energy into space just as it always has. If you were observing it casually, without instruments, without long-term data, you might not suspect anything unusual at all. But inside, the situation is changing in ways that leave traces. Not loud ones, not obvious ones, but quiet signals that the balance we talked about earlier is becoming strained. One of the first things to understand here is that the core of the star is no longer a simple place. Earlier in its life, when hydrogen fusion dominated, the structure was relatively straightforward. A central core where fusion occurred, surrounded by layers that transported energy outward. That simplicity made stability easier to maintain. But now, as the star has moved through multiple stages of fusion, the core has become layered. Different shells exist at different depths, each fusing different elements. Hydrogen might still be fusing in an outer shell, beneath that helium is fusing. Deeper still, heavier elements like carbon, oxygen, neon, and others may be undergoing fusion in their own regions. It becomes a kind of nested structure, almost like layers of an onion. And each layer operates under slightly different conditions, different temperatures, different pressures, different rates of energy production. At first, this layered structure functions well enough. Each shell contributes to the overall outward pressure, helping to counteract gravity. But as heavier elements begin to dominate the inner layers, the efficiency of these processes declines. Fusion of heavier elements produces less energy relative to the effort required to maintain it, which means the star has to work harder to achieve the same effect. Now, here's where the quiet warning signs begin to appear. The star starts to lose its ability to regulate itself smoothly. Earlier, if fusion slowed slightly, gravity would compress the core, raising the temperature, which would increase fusion again. It was a stable feedback loop. Small changes corrected themselves. But in this later phase, the feedback becomes less reliable. The adjustments are no longer smooth. Instead of steady regulation, the star begins to experience fluctuations. These fluctuations can show up as small changes in brightness, not massive flickers, not anything that would make the star blink on and off, but slight variations. The kind that would only become clear if you were carefully measuring the star over time. It's as if the star is no longer perfectly steady. There's a slight irregularity to its output, and that irregularity reflects what's happening deep inside. Another sign comes from the way the outer layers behave. As the core becomes denser and hotter, the outer regions can expand and contract in response. These changes are not violent, but they can alter the star's size and surface temperature over time. So the star might grow larger, then stabilize, then shift again. From a distance, these changes might look like a slow pulsing. Again, not dramatic, not rapid, but noticeable if you track it long enough. These pulsations are a sign that the internal structure is no longer in perfect equilibrium. The star is adjusting, trying to maintain balance, but doing so with increasing difficulty. There's also something happening in the core that doesn't directly show itself at the surface, but is incredibly important. The production of neutrinos. Neutrinos are tiny, nearly massless particles that are produced in large numbers during certain nuclear reactions. They interact very weakly with matter, which means they can escape from the core of a star almost instantly, carrying energy away with them. In earlier stages of a star's life, energy primarily leaves the core in the form of radiation, which takes a long time to travel outward. But in these later stages, neutrino production becomes significant, and because neutrinos escape so easily, they effectively remove energy from the core without contributing to the outward pressure that supports the star. So the core begins to lose energy more rapidly, not in a way that you would see directly, but in a way that affects the internal balance. It's like a system that is quietly leaking energy, and that leak makes it harder to maintain stability. At the same time, the composition of the core continues to change. Heavier and heavier elements build up, moving the star closer to a critical point. And here, the timeline begins to compress. Earlier stages lasted millions or billions of years, but these later stages can pass much more quickly. Fusion of carbon might last hundreds or thousands of years. Neon fusion could last only a few years. Oxygen fusion, perhaps months. And the final stages, where silicon fuses into iron, can occur over the course of days. Days. After millions of years of relative stability, the star suddenly finds itself moving through its final phases at an accelerated pace. And yet, from the outside, it still looks like a star. This is one of the more striking aspects of this stage. The most important changes are happening deep within the core on timescales that are short compared to the star's overall life, but still not immediately visible from the outside. So the star continues to shine, continues to exist, even as it approaches a point where it can no longer support itself. There's also an increasing imbalance between the different layers. Each shell of fusion produces energy at its own rate, and these rates can fluctuate independently. This can create instabilities, where one layer expands while another contracts, leading to complex internal motion. It's no longer a simple, well-regulated system. It's a dynamic, shifting structure, trying to maintain balance but struggling to do so. And then there's the core itself. As heavier elements accumulate, the core becomes more and more dense. The pressure increases, the temperature rises. But unlike earlier stages where higher temperature meant more fusion and more outward pressure, this stage is different. Because the final product of these fusion processes is iron. And iron changes everything. Fusion of iron does not release energy, it consumes it. So once the core is dominated by iron, the star loses its ability to generate the outward pressure needed to counteract gravity. And this is perhaps the most important warning sign of all. Not something visible, not something that creates a flash or a pulse, but a fundamental change in the star's ability to sustain itself. Up until this point, fusion has always been the star's way of resisting collapse. Now that mechanism is gone, or at least it's no longer effective, so the star enters a state where gravity is no longer being fully opposed, and that changes the entire situation. The quiet warning signs we've been talking about, the fluctuations, the pulsations, the energy lost through neutrinos, all of these are leading toward this moment. A moment where the balance is no longer just slipping, it's failing. But even then, there is no immediate explosion, no sudden outward burst. What comes next is not an explosion at first, it's something else, something inward, something incredibly fast. Because once the core can no longer support itself, gravity doesn't hesitate, it acts. And when it does, the slow changes that have been building for so long give way to something much more sudden. Something that unfolds not over millions of years, not even over days, but in a fraction of a second. Up until now, every time the star drifted slightly out of balance, it found a way to compensate. Fusion would slow, gravity would compress the core, temperature would rise, and fusion would pick up again. It was a reliable cycle, one that kept the star stable for most of its life. But that cycle depends on one crucial condition. Fusion must be able to respond, and now it can't. Deep in the core, the composition has reached a stage where the usual rules no longer apply. The build-up of heavier elements, especially iron, has quietly removed the star's last reliable source of outward pressure. Fusion, which once acted as a counterweight to gravity, is no longer able to carry that role. So when gravity presses inward now, there's no equal response pushing back, and this is where things begin to feel different. Not dramatic at first, not explosive, but decisive. Gravity starts to win. It's not a sudden takeover in the sense of a single moment. It's more like a tipping point that has been approached slowly, and then, once crossed, everything begins to move in one direction. Inward. The core, which has already been contracting in small adjustments over time, now begins to contract more seriously. The pressure increases rapidly. The density rises. Matter is packed closer and closer together, and because compression raises temperature, the core becomes even hotter. But this time, the increase in temperature doesn't lead to a stabilizing effect. There's no new stage of fusion waiting to rescue the star. No additional process that can suddenly generate enough energy to counteract the inward pull. Instead, the rising temperature contributes to a series of processes that actually make things worse. One of the first of these is something called photodisintegration. At these extreme temperatures, the photons, the particles of light inside the core, become so energetic that they can break apart atomic nuclei. Iron nuclei, which had been built up through earlier fusion stages, start to fall apart into smaller components. This might sound like a minor detail, but it has a significant consequence. Breaking apart these nuclei absorbs energy, so instead of generating outward pressure, the core is now losing energy even faster. It's like trying to maintain a balance while your support system is not only failing, but actively draining what little energy remains. At the same time, another process begins to take over. As the density increases, electrons are forced closer and closer to atomic nuclei. Under normal conditions, electrons orbit nuclei at a comfortable distance. But in this environment, there is no space for that arrangement. The electrons are pushed into protons, and when that happens, they combine to form neutrons. This process is called electron capture, and it has two important effects. First, it reduces the number of electrons available to provide what's known as electron degeneracy pressure, one of the forces that can help resist collapse in dense matter. As electrons disappear into protons, that source of pressure weakens. Second, it produces neutrinos. And as we touched on earlier, neutrinos escape almost instantly, carrying energy away from the core. So now the core is losing energy through multiple channels. Photodisintegration is consuming energy. Neutrinos are carrying energy away. Fusion is no longer providing enough energy to compensate, and gravity continues to pull inward, unopposed. At this point, the situation is no longer stable in any meaningful sense. The core is collapsing, not slowly, not in the gradual way it has adjusted before, but rapidly. The timescale changes dramatically here. What once took millions of years now unfolds in seconds. The core's radius shrinks at an incredible rate. Material that was once spread over a vast region is compressed into a much smaller space. The density becomes extreme, far beyond anything we encounter in everyday experience. To get a sense of it, imagine the mass of the sun compressed into a sphere only a few tens of kilometers across. That's the kind of density we're talking about. And as the core collapses, the speed of the infalling material increases. Gravity accelerates everything inward. There's no longer a balance, no longer a back and forth between forces. It's a one-way process, inward, faster and faster. And yet, even in this rapid collapse, there is still structure to what's happening. The outer layers of the star are not collapsing at the same rate as the core. They are still relatively unaffected at first, still supported by the processes happening in the layers above the core. So for a brief moment you have a situation where the core is collapsing rapidly, while the outer regions remain in place. It's a kind of separation of behaviour. The centre is falling inward, while the rest of the star hasn't yet responded fully. But that won't last, because as the core collapses, it creates conditions that will soon affect the entire star. The density in the core continues to rise, the particles are packed closer together, and eventually they reach a point where they can't be compressed any further in the usual way. This is where something new comes into play: neutron degeneracy pressure. Just as electrons can provide a kind of pressure when they are packed closely together, neutrons can do the same. But this pressure only becomes significant when matter is compressed to extremely high densities. As the core becomes dominated by neutrons, this pressure begins to build, and for a brief moment it acts as a resistance. The collapse slows, and then it stops, not gradually but abruptly. The inward motion of the core is halted, and all the material that was falling inward at incredible speeds suddenly has nowhere to go. This is the point where everything changes again, because when that inward motion is stopped so suddenly, the energy has to go somewhere, and it does, outward. The core rebounds. It's not a gentle push, it's a powerful, sudden reversal of motion. The collapsing material slams into the newly stiff core, and the result is a shock wave. That shock wave begins to move outward, through the layers of the star, and this is the moment where the story shifts from collapse to explosion. But it's important to pause here for just a moment, before following that shockwave outward, because what we've just seen is not simply a star failing. It's a process where gravity, which has always been present, finally becomes the dominant force. For most of the star's life, gravity was balanced by fusion. Then, as fuel ran low, the balance became harder to maintain. And now, with fusion no longer able to respond, gravity takes over completely. It pulls everything inward, compresses the core, and sets the stage for what comes next. For almost the entirety of a massive star's existence, change has been slow. Adjustments happened over millions of years. Imbalances were corrected gently. Even when things began to slip, there was still time, still a sense of gradual movement from one state to another. But now, that pace disappears. What was once slow becomes incredibly fast, and it all centres on the core. Up to this point, the core has been resisting gravity in one way or another, first through fusion, then through layers of pressure and increasingly complex reactions. Even as those mechanisms weakened, they still offered some resistance, some delay. Now, that resistance is gone. Gravity doesn't wait. Once it is no longer opposed, it acts immediately and without hesitation. The core begins to collapse, not in the measured way it did before, not as a slight contraction followed by stabilization, but as a rapid inward acceleration. Matter, that was once in a delicate balance, now falls freely toward the center, pulled by an overwhelming gravitational force. The speed of this collapse is difficult to imagine. We're not talking about something that unfolds over hours or even minutes. The core can shrink dramatically in less than a second. Material is moving inward at a significant fraction of the speed of a light. Every layer is being pulled toward the center with increasing urgency. It's no longer a system adjusting itself, it's a system failing. As the core collapses, the density rises sharply. Atoms are crushed together. The space between particles disappears. The familiar structure of matter begins to break down under the extreme pressure. Electrons, which once orbited atomic nuclei, are forced into them. Protons and electrons combine. Neutrons are formed. This transformation happens on a massive scale, converting the core into something fundamentally different from what it was before. What was once a collection of atoms becomes a dense, neutron-rich mass. And as this process unfolds, neutrinos are produced in enormous numbers. They stream out of the core almost immediately, carrying away energy. Trillions upon trillions of them pass through the outer layers of the star and into space, barely interacting with anything along the way. For a brief moment, the star becomes one of the most intense sources of neutrinos in the universe. But inside, the collapse continues. The core shrinks further, the density increases, and the inward motion accelerates. At this stage, the collapse feeds on itself. The stronger the gravity becomes, the faster the material falls inward. The faster it falls, the more energy is released as it compresses, and the more extreme the conditions become. There's no longer any mechanism left to slow it down, no fusion process to push outward, no stable pressure to hold things in place, only gravity. And then, suddenly, the situation changes again. As the core becomes incredibly dense, a new form of resistance emerges: neutron degeneracy pressure. Just as electrons resist being squeezed too closely together due to quantum mechanical principles, neutrons do the same. But this resistance only becomes significant at extremely high densities, the kind reached during this collapse. When that density is reached, the collapse cannot continue in the same way. The inward motion is halted, abruptly. Imagine material falling inward at tremendous speed, only to encounter a region that cannot be compressed any further. The result is not a gentle stop, it's a violent one. The core essentially slams to a halt, and when that happens, all the energy of the collapse has to go somewhere. It rebounds. The inner core stiffens, resisting further compression, and the infalling material crashes into it. This collision creates an enormous pressure wave that travels outward. This is the birth of the shock wave. It begins deep within the star, at the boundary where the collapse has been stopped. From there, it moves outward, pushing against the layers of material that are still falling inward. At first, this shock wave is incredibly powerful. It surges outward, carrying energy from the collapsed core into the rest of the star. But the situation is not simple, because the outer layers are still collapsing inward at the same time, so you have two opposing motions: material falling inward under gravity, and a shock wave trying to move outward against that flow. This creates a complex interaction. The shock wave loses energy as it moves outward. It has to push against the infalling material, and in doing so, it begins to weaken. In some early models of supernova, it was thought that this shock wave might stall, failing to produce a full explosion. But in reality, something helps it, and that something comes from the neutrinos. Those neutrinos that were produced in vast numbers during the collapse don't all escape immediately. Some of them interact with the material just outside the core, depositing energy into it. This additional energy helps to revive the shock wave. It gives it the boost it needs to continue moving outward, and once it regains strength, it becomes unstoppable. It pushes through the layers of the star, heating them, accelerating them, and eventually driving them outward in a massive explosion. But that explosion, the bright visible event we call a supernova, is still just ahead. Right now, we're at the moment where the core has collapsed and rebounded. A moment that lasts less than a second, yet determines everything that follows. It's a transition from inward motion to outward motion, from collapse to explosion. And it's worth pausing here, just briefly, to take in how sudden this change is. For millions of years, the star has been evolving slowly, adjusting, balancing. Then, in a fraction of a second, the core collapses, matter transforms, and a shockwave is born. It's not a gradual ending, it's a sudden shift, a turning point where the entire structure of the star is redefined. And from this point onward, the story is no longer about maintaining balance, it's about what happens when that balance is gone. The shockwave continues to move outward. The outer layers begin to respond. Long before any light escapes, before anything becomes visible across space, there is a moment that defines everything that follows. It does not last long. In fact, It is over almost as soon as it begins. And yet, within that fraction of a second, the fate of the star is decided. Up until now, we've followed a process that gradually lost stability. The balance weakened, gravity took over, and the core began collapsing. That collapse accelerated quickly, compressing matter to extreme densities and triggering reactions that stripped away the last forms of resistance. Now, we arrive at the point where that inward motion reaches its most intense state. Everything is falling toward the center. Every layer of the core is moving inward at incredible speed, pulled by gravity that has finally gained complete control. There is no longer any outward pressure strong enough to counteract it, no stabilizing mechanism left to slow the descent. It's important to notice something here. Even though we often talk about stars exploding, the first decisive event is actually the opposite. It's an implosion. The star doesn't begin by blowing apart. It begins by collapsing inward, more rapidly than at any point in its entire existence. And this inward collapse is not uniform in a simple way. The very center of the core, the innermost region, begins to behave differently from the outer parts. As density rises, the inner core reaches a point where it becomes incredibly stiff, dominated by neutron-rich matter that resists further compression. But just outside that inner core, material is still falling inward. So you end up with a situation where the inner core is slowing down, approaching a limit, while the outer core continues accelerating inward. This difference creates tension, a kind of mismatch in motion, and that mismatch builds rapidly. The infalling material does not gently settle onto the core, it crashes into it. At this stage, speeds are so high and density so extreme that the collision is not like anything we encounter in ordinary conditions. It is more like a sudden, overwhelming compression of matter into a space that cannot accommodate it. The inner core resists. The outer layers keep coming, and in that instant the collapse reaches its peak. This is the moment of implosion, the point where the inward motion has gone as far as it can. The core cannot be compressed further in the same way. The physical properties of matter, particularly neutron degeneracy pressure and nuclear forces, create a hard limit. Beyond this, the rules change. So when the infalling material reaches this boundary, it doesn't continue inward. It stops, violently, and that sudden halt is crucial, because everything that was moving inward at immense speed now has nowhere to go. Momentum doesn't simply disappear. Energy doesn't vanish. Instead, it is redirected. In that instant, the implosion turns into something else. The inner core, having resisted further compression, acts almost like a surface. The collapsing material slams into it, and the energy of that motion is converted into pressure. That pressure builds rapidly, and then it releases outward. This transition happens incredibly quickly. There is no long pause between collapse and rebound. One moment, everything is falling inward. The next, a shock wave is forming, pushing outward from the core. But right at the boundary between those two states, there is a brief, almost imperceptible moment where everything is compressed to its limit. The density is extreme. The temperature is unimaginably high. And the conditions are unlike anything else in the universe outside of neutron stars or black holes. It's difficult to fully picture what that means. Matter, as we normally understand it, no longer behaves in familiar ways. Atoms have been dismantled. Nuclei are packed tightly together. The distinction between individual particles becomes less meaningful in the face of such density. It is, in a sense, the most compact state the star can achieve without crossing into something even more extreme. And then, just as quickly as it reached that state, it begins to change again. The rebound starts. Now, something else is happening at the same time. Throughout the collapse, neutrinos have been produced in enormous quantities. These particles, created as electrons combine with protons to form neutrons, carry away energy from the core. Most of them escape almost immediately, passing through the star with barely any interaction, but not all. Some of these neutrinos interact with the material just outside the core, transferring energy into it. This process becomes important in the moments following the implosion, as it helps energize the outward moving shockwave. So while the implosion itself is a moment of inward collapse reaching its limit, it is also the setup for everything that follows. It defines the starting conditions for the explosion. It determines how much energy is available. It shapes the structure of the core that remains behind, and it sets the stage for the outward motion that will soon dominate. From the outside, none of this is visible yet. There is no flash of light, no sudden brightening in the sky. All of this is happening deep within the star, hidden beneath layers of gas that have not yet responded to the changes at the centre. But the transformation is already underway. The star, which has spent millions of years maintaining its structure, has now undergone a fundamental shift. Its core has collapsed, reached a limit, and rebounded. And in doing so, it has created the conditions for one of the most energetic events in the universe. It's worth noticing how abrupt this transition is. For most of the star's life, everything has been gradual. Changes unfolded slowly. Processes took immense amounts of time. But here, at the end, everything accelerates. The implosion itself happens in less than a second. A lifetime of gradual evolution leads to a moment of sudden transformation. And once that moment passes, the direction of motion changes completely. The inward collapse gives way to an outward force. The shockwave begins to move through the star. Not long ago, everything was moving inward. Matter was falling toward the centre at incredible speed, pulled by gravity that had finally taken full control. The core had collapsed, reached its limit, and for a brief moment all motion pointed in a single direction. But that direction does not last, because once the inner core reaches a state where it can no longer be compressed, the story shifts. The inward collapse doesn't simply stop and fade away. It changes character. The motion that had been building for so long, gathering speed and energy, suddenly encounters resistance, and when something moving that fast is stopped, the result is never quiet. The core halts, and then it pushes back. This is the rebound. It happens almost immediately after the implosion reaches its peak. The inner core, now incredibly dense and dominated by neutron-rich matter, behaves differently than it did even moments before. It has become stiff in a physical sense, resistant to further compression. So when the outer layers of the collapsing core slam into it, they do not pass through. They bounce, not in a gentle or orderly way, but with a force that reflects the energy of everything that came before. All the inward motion, all the gravitational acceleration, all the compression is suddenly redirected outward. And that redirection creates something new, a shock wave. It begins deep inside the star, right at the boundary where the collapse has been stopped. At first, it is just a region of intense pressure, moving outward faster than the surrounding material can adjust. But as it travels, it becomes more defined. It becomes the beginning of the explosion. Now, it's important to understand that this shockwave does not move into empty space. It is travelling through the star itself, through layers of gas that are still, in many cases, moving inward. So the situation is complex. You have material falling inward under gravity, and at the same time you have a shockwave pushing outward. These two motions collide. The shockwave must fight its way through the star. At first, it has the advantage. The energy from the collapse is enormous, and the initial outward push is strong. The shockwave moves quickly, compressing and heating the material in front of it as it goes. But this is not a simple, uninterrupted expansion. As the shockwave travels outward, it loses energy. Each layer of the star it passes through absorbs some of that energy. The material is heated, ionized, and pushed outward, but the process takes a toll. The shockwave slows down. There is a moment, not long after the rebound begins, where it looks like the shockwave might stall, like it might not have enough energy to fully escape the star. This is a delicate point, because if the shockwave were to stall completely, the star might not explode in the way we expect. The outer layers might not be expelled. The event would be very different from what we call a supernova, but something helps the shockwave, something that has been building quietly throughout the collapse: neutrinos. During the implosion, as electrons were forced into protons and neutrons formed, vast numbers of neutrinos were produced. These particles, almost massless and barely interacting with matter, streamed out of the core in all directions. Most of them escape without affecting anything, but not all. A small fraction of those neutrinos interact with the material just outside the core, and when they do, they deposit energy. That energy becomes crucial. It provides an additional push to the shockwave, helping to revive it, to strengthen it, to keep it moving outward when it might otherwise fade. It's a subtle contribution, but an essential one. Without it, the explosion might not happen in the same way. With it, the shockwave regains strength, and once it does, the outward motion becomes unstoppable. The shockwave accelerates again, pushing through the remaining layers of the star. It carries with it not just the energy of the rebound, but also the additional energy provided by neutrino interactions. The star begins to tear itself apart, from the inside outward. Layers that have been held together by gravity for millions of years are suddenly lifted, accelerated and driven outward at immense speeds. The structure that once defined the star begins to break down. And this is the moment where the explosion truly begins. Not as a single flash, not as an instantaneous event, but as a process. The shockwave continues to move outward, and as it does, it transfers energy to the outer layers of the star. Those layers heat up dramatically, reaching temperatures that allow for further nuclear reactions. New elements are formed in this process, heavier ones, created in the extreme conditions of the explosion itself. But we'll come back to that later. For now, what matters is the motion. Outward. Everything that was once stable is now being driven away from the centre. The star is no longer a single, cohesive object. It is becoming a rapidly expanding cloud of material. From far away, this process begins to show itself as a sudden increase in brightness. The star, which may have been a relatively ordinary point of light before, suddenly becomes much brighter. As the shockwave reaches the surface and the outer layers are expelled, the energy released is enormous. For a time, the star can outshine entire galaxies. But even as that brightness grows, the process is still unfolding. The shockwave is still moving. The material is still accelerating outward. And at the centre, something new is formed. The core that collapsed and rebounded does not disappear. It remains. Depending on its mass, it may become a neutron star, an incredibly dense object where matter is packed so tightly that a teaspoon of it would weigh billions of tons, or if the mass is great enough, the collapse may continue even further, forming a black hole. But regardless of the exact outcome, the core is no longer the same as it was before. It has been transformed, and it now sits at the centre of an expanding explosion. Meanwhile, the outer layers continue to move outward, driven by the energy of the shockwave. They carry with them the elements that were formed during the star's life, as well as those created in the explosion itself. These materials spread out into space, forming a cloud that will continue to expand for thousands of years. But at this moment, we are still close to the beginning of that expansion. The shockwave is still fresh. The outward motion is still gaining momentum, and the star, which once existed in a state of balance, is now fully committed to a different path. It is no longer trying to hold itself together, it is coming apart. And this transition, from inward collapse to outward explosion, is one of the most important steps in the entire process, because it is the point where everything changes direction, where gravity's victory over fusion leads not just to collapse, but to a release of energy that reshapes the star completely. It's also a reminder of how quickly things can change at the end. For millions of years, the star evolved slowly. Then, in less than a second, the core collapsed and rebounded. And now, in the moments that follow, the explosion begins to unfold, sending material outward into space, But even though we can now call it an explosion, it's not yet the full picture. The shockwave has begun its journey, but it still has to travel through the entire star. It still has to reach the surface. Unlike everything that came before, there is no sense of patience left in the system now. For most of its existence, the star adjusted slowly. Even when instability began to creep in, the changes were measured, layered, almost careful in the way they unfolded. But once the rebound has happened and the shockwave has formed, that long history of gradual evolution gives way to something entirely different. Now, everything is moving. Fast. The shockwave that was born deep within the core does not linger. It doesn't pause to stabilize or reorganize. It travels outward immediately, carrying with it the energy released during the collapse and rebound, pushing into regions of the star that, until moments ago, had no idea anything had changed. And that contrast is important, because while the core has already undergone a complete transformation, the outer layers are still, in a sense, living in the past. They are still structured the way they were before the collapse began, still held together by the same forces that maintain the star for millions of years. For a brief time, there is a disconnect. The centre has changed completely. The outside has not. The shockwave is what bridges that gap. As it moves outward, it acts like a messenger carrying news that cannot be ignored. It compresses the material ahead of it, heating it, accelerating it, and forcing it to respond to conditions that are far more extreme than anything it has experienced before, and it does all of this at incredible speed. Not the speed of light, but still fast enough that, on the scale of the star, it moves with remarkable urgency. Layers that once took thousands of years to evolve are now being reshaped in seconds. The shockwave is not a gentle wave. It is a boundary between two states. Behind it, material has been heated, energized, and set into outward motion. Ahead of it, material is still in its original state, or in many cases still falling inward. So as the shockwave advances, it creates a sharp transition. Everything it touches changes. The gas it passes through is compressed to higher densities. Its temperature rises dramatically. Atoms are stripped of their electrons, becoming ionized. In some regions, nuclear reactions are triggered by the sudden increase in temperature and pressure, creating new elements in the process. All of this happens in an instant, and yet the shockwave itself is not immune to the conditions it encounters. As it travels outward, it must push against the inertia of the material ahead of it. That material has mass, and moving it requires energy. So with every layer the shockwave passes through, it loses some of its strength. This is not a simple, uninterrupted expansion. It's a struggle. The shockwave pushes outward. The surrounding material resists. Energy is transferred but also dissipated. And for a time, it is not entirely clear which side will dominate. Earlier, we touched on the idea that the shockwave might stall. This is the stage where that possibility becomes real. As it moves outward, the shockwave slows. The energy it carries is being spread out, used to heat and move the star's outer layers. Without additional support, it could lose momentum, but this is where the processes happening near the core continue to matter. Even as the shockwave moves outward, neutrinos are still being produced and escaping from the dense core, and some of those neutrinos interact with the material just behind the shockwave, depositing energy into it. That energy acts like a reinforcement. It strengthens the region behind the shockwave, giving it the extra push needed to keep moving forward. So instead of stalling, the shockwave regains momentum. It becomes more effective, more capable of pushing through the remaining layers of the star. And as it does, the structure of the star begins to break down more completely. The outer layers, which once rested in a stable configuration, are now being lifted and accelerated outward. The gravitational hold that kept them in place is being overcome by the energy of the shockwave. It's not a single, uniform motion. Different layers respond in slightly different ways. Some are accelerated more quickly, others lag behind. The result is a complex pattern of motion, with material expanding outward at varying speeds. If you could observe this process from close by, it would not look like a perfectly smooth sphere expanding evenly in all directions. It would look turbulent, uneven, full of motion and interaction. But from a distance, the overall effect is clear. The star is coming apart. And as the shockwave continues to move outward, it approaches the outermost layers. These layers are less dense than the core regions, which changes how the shockwave behaves. With less resistance, it can accelerate again, moving more freely as it nears the surface. And this is where the transition from internal event to visible phenomenon begins. Up until now, everything has been happening beneath the surface, hidden. But as the shockwave reaches the outer layers, it begins to carry energy to regions that can radiate it into space more directly. The outer layers heat up rapidly, their brightness increases. And when the shockwave finally reaches the surface, the energy it has been carrying is released outward in a way that can be seen across vast distances. But even before that moment, the internal changes are profound. The star structure has been completely disrupted. The layered arrangement that developed over millions of years is no longer intact. The boundaries between different regions are being erased as material is mixed and driven outward. Elements that were once confined to the core are now being carried toward the surface. And this mixing has consequences, because it allows the products of the star's internal processes to be distributed more widely, both within the explosion itself and eventually into the surrounding space. But again, that is something we will follow a bit later. For now, the focus remains on the motion. The shockwave is still travelling, still pushing outward, still reshaping everything it encounters. And with each layer it passes through, the star moves further away from its former state. It is no longer a stable, balanced object. It is an expanding system, driven by energy that was released in a single, sudden event. From far away, there is no warning, no gradual brightening that hints at what is about to happen, no slow signal that something deep inside the star has already changed beyond repair. One moment, the star looks ordinary, just another point of light among countless others, and then, suddenly it doesn't. It brightens. Not a little, not in the subtle way stars sometimes fluctuate, but dramatically. Enough to stand out. Enough to draw attention even across vast distances. In some cases, enough to rival the combined light of billions of other stars in the same galaxy. And that is the moment when everything that has been happening inside finally becomes visible. Up until now, the collapse, the rebound, and the racing shockwave have all been hidden beneath layers of gas. Even as the star was tearing itself apart from the inside, nothing about its appearance gave that away. But the shockwave has reached the surface, and when it does, it carries with it an enormous amount of energy that has been building since the core collapse began. That energy has to go somewhere, so it moves outward. As the shockwave breaks through the outer layers, it heats them rapidly. Temperatures rise to levels far beyond anything the surface of the star has experienced before. The gas becomes extremely hot, extremely energetic, and begins to radiate light with incredible intensity. This is often called shock breakout. It's the point where the energy that was trapped inside the star is finally released into space, and it happens quickly. In a very short time, the brightness of the star increases by an enormous factor. A star that might have been barely visible to distant observers can suddenly become one of the brightest objects in the sky. For a while, it can outshine entire galaxies. That might sound like an exaggeration at first, but it isn't. A galaxy contains billions of stars, each shining steadily. But most of those stars are relatively small or distant, contributing modest amounts of light. A supernova, on the other hand, releases a vast amount of energy all at once. So even though it comes from a single star, its brightness can temporarily exceed the combined light of all the stars around it. It's not because the star suddenly became larger or more massive, it's because of how quickly and how intensely the energy is released. Now it's worth slowing down here for a moment, because this brightness is not the explosion itself. It's the visible result of processes that have already happened. The core has already collapsed. The rebound has already created the shockwave. The shockwave has already travelled through the star. What we are seeing now is the aftermath of all of that. The energy reaching the surface, the outer layers heating up and radiating light. And this light does not just appear and disappear instantly. After the initial shock breakout, the brightness continues to evolve. The outer layers of the star are still expanding, still moving outward at high speeds. As they expand, they cool, but they also continue to radiate energy. The brightness rises to a peak, and then gradually begins to decline over time. This can take days, weeks, or even months, depending on the details of the explosion. So the supernova is not just a flash, it is a sustained event, a bright, evolving source of light that can be observed and studied from across the universe. And during this time, something else is happening within the expanding material. The explosion has created new elements. Earlier in the star's life, fusion built up heavier elements in the core. But the conditions during the explosion itself are even more extreme. Temperatures and pressures are high enough to drive nuclear reactions that cannot occur under normal stellar conditions. Elements heavier than iron can be formed in this environment. Gold, uranium, and many others. These elements are created in the chaos of the explosion and then carried outward with the expanding debris. But from the perspective of an observer, what stands out first is the light, the sheer brightness of it, and the fact that it appears so suddenly. Historically, this has been recorded many times. Ancient astronomers would look up at the night sky and notice a new star that hadn't been there before. They called them guest stars because they appeared unexpectedly, stayed for a while and then faded away. What they were seeing were supernovae, events happening far away, but bright enough to be visible even without modern instruments. One of the most famous examples occurred in 1054 when a supernova was observed in the constellation Taurus. It was so bright that it could be seen during the day for weeks. What remained after that explosion is now known as the Crab Nebula, a cloud of expanding gas that still carries the imprint of that event. But in the moment itself, for those observers, it would have been just a sudden, bright point of light, something new in the sky. And that sudden appearance is one of the defining characteristics of a supernova. Even though the processes leading up to it take millions of years, the visible change happens quickly, which can make it feel almost instantaneous. Now, there is something else to consider about this brightness. It is not uniform. Different supernovae can have different peak brightness levels, depending on the type of star and the details of the explosion. Some are brighter than others, some fade more quickly, some have more complex light curves, with multiple peaks or variations over time, but the general idea remains the same: a rapid increase in brightness, a peak, and then a gradual decline, and during that decline the expanding material continues to spread out into space. The star is no longer a single object, it has become a cloud of gas and newly formed elements moving outward at high speeds, and at the centre of that cloud the remnant of the core remains, either a neutron star or a black hole depending on the mass. But again, from far away, what matters first is the light, the sudden, intense brightness that marks the event, and that brightness serves as a signal that something significant has happened, that a star has reached the end of its life, that energy has been released on a massive scale, and that material has been sent out into space, where it will eventually become part of something else. So when we talk about a supernova being brighter than an entire galaxy, we're really talking about this moment. The moment when all the energy that has been building inside the star is released in a way that can be seen across vast distances. A moment that is brief compared to the star's lifetime, but incredibly powerful. And yet, even as that light spreads outward, even as it travels across space and reaches distant observers, the story is still continuing. Because the expanding cloud of material is still moving, still interacting with the surrounding environment, still carrying with it the elements that were created during the star's life and its final explosion. And as that cloud expands, it begins to take on new forms, structures that can be observed long after the initial brightness has faded, shapes that reflect the dynamics of the explosion and the environment around it. So while the light marks the beginning of the visible event, it is not the end of the process. It is simply the first thing we notice, the first sign that the star has transitioned from a stable, long-lived object into something entirely different. And as that light begins to fade, what remains becomes the focus, the expanding remnants, the structures left behind, and the clues they carry about what happened deep inside the star. Step outside on a quiet night, look up, and for the most part the sky feels familiar. The same constellations, the same steady points of light, the same sense that everything up there is distant, calm and unchanging. Even if you don't know their names, the stars seem reliable, predictable. But imagine just for a moment that something changes. Not gradually, not over months or years, but suddenly. You look at a patch of sky you've seen 100 times before, and there, where nothing unusual stood out yesterday, is a new point of light. Bright, clear, impossible to ignore. At first you might think it's a planet, or maybe an aircraft, or something closer to home, but it doesn't move the way those things do. It stays fixed among the stars, and it keeps shining. This is what a supernova would look like from Earth. Not as a slow build-up, not as a visible explosion in the way we might picture fireworks or something expanding outward in real time, but as a sudden appearance of brightness, a star that either wasn't visible before or was so faint that no one paid attention to it, now shining with a clarity and intensity that stands out immediately. And the scale of that brightness can vary. If the supernova happens in a distant galaxy far beyond our own, it might appear as just a small point of light, visible only with telescopes. Still significant to astronomers, still measurable, but not something you would notice with the naked eye. But if it happens closer, within our own galaxy, the experience becomes very different. Some supernovae in our galaxy could be bright enough to rival the brightest stars in the sky. Others could be so bright that they are visible during the day, appearing as a pale but noticeable point of light even against the brightness of the sun. That has happened before. Historical records describe new stars that appeared suddenly and were visible in daylight for weeks. Observers at the time had no way of knowing what they were seeing in terms of stellar physics, but they knew something unusual had occurred. From Earth, the experience would not feel like witnessing an explosion in motion. Even though the event itself is dynamic and violent, the distance is so vast that what we see is the integrated light arriving at our eyes. The expansion of the star's outer layers happens too far away and too quickly to be resolved in real time without instruments, so instead of seeing something grow or burst, you see a star brighten and stay bright. Over the course of days, the brightness increases, reaching a peak. During that time, the object becomes more noticeable, more dominant in that region of the sky. It draws attention, even from casual observers. Then, slowly it begins to fade. Not immediately, not abruptly, but gradually. Night after night, if you were to observe it carefully, you would notice that it becomes a little dimmer. The change might be subtle from one evening to the next, but over weeks it becomes clear. The star that suddenly appeared is now diminishing, and over time it fades back into obscurity. But that fading light is only part of the story, because even as the brightness changes, the nature of the light itself can tell us more about what's happening. With telescopes, astronomers can analyze the light coming from a supernova, breaking it into its component wavelengths. This reveals patterns, lines that correspond to different elements and physical conditions. From those patterns, it's possible to determine what the star was made of, how fast the material is moving, and what processes are taking place in the expanding cloud. But without instruments, without analysis, the experience remains simple. A new light appears, it shines, and then it fades, there's something quietly striking about that. Because while the physical processes behind a supernova are incredibly complex, the human experience of it is straightforward. You don't see the collapse of the core, you don't see the shock wave racing outward, you don't see the formation of new elements, you just see the result, a change in the sky. Now it's worth considering something else, the timing. When we observe a supernova from Earth, we're not seeing it as it happens in real time at its location. Light takes time to travel, so if a star explodes in our galaxy, say thousands of light years away, the light from that event takes thousands of years to reach us. By the time we see it, the event itself has already happened long ago. We are seeing the past. A snapshot of something that occurred at a distant point in time, which means that when a supernova appears in our sky, it's not something that just happened in that moment. It's something that happened long ago, and the light has only just arrived. This adds another layer to the experience. You're not just observing a distant event. You're observing a distant event from the past, arriving at your present. And yet, it feels immediate, because the light reaches you now. Now, let's consider what would happen if a supernova occurred relatively close to Earth. Not dangerously close, but close enough to be easily visible. The brightness could be significant. It might cast shadows at night. It might be visible even when the moon is up. It could become one of the brightest objects in the sky, second only to the sun and the moon, and for a time, it would be a constant presence. Visible night after night, slowly changing, slowly fading. People would notice. It would become a point of curiosity, something discussed, something observed. But it would not feel threatening. Not unless it were extremely close, which is rare. Most supernovae occur at distances where their effects are primarily visual for us. The energy is immense, but space is vast, and that distance reduces the impact. So what we experience is the light, the brightness, the appearance of something new in a sky that usually feels unchanging. And then, as the weeks pass and the light fades, the sky returns to its familiar pattern. The constellations remain, the steady stars continue to shine, and the place where the supernova appeared becomes just another point among many. But if you had been watching closely, you would know that something significant had happened there, that a star had ended its life, that energy had been released on a massive scale, and that material had been sent out into space, even if you couldn't see that part directly. Because long after the light fades, the remnants of the explosion remain, expanding clouds of gas, slowly spreading out, interacting with the surrounding space. But those remnants are not visible to the naked eye in most cases. They require instruments, careful observation, and time. So from a human perspective, the experience of a supernova is brief, a sudden brightening, a period of visibility, and then a gradual return to normal. And yet, behind that brief experience lies a process that took millions of years to unfold, a process that reshaped the star completely, a process that created new elements and sent them into space. So the next time you look up at the night sky, it's worth remembering that while most stars appear steady and unchanging, some of them are not. Some of them are moving toward an ending that, when it arrives, will briefly outshine everything around them. And if one of those events were to become visible from Earth, it wouldn't look like a distant explosion unfolding in real time. It would look like a new light, a quiet, steady point in the sky that wasn't there before, one that slowly fades, leaving behind a story that continues long after the brightness is gone. If you were to watch enough of these events over time, not just one or two, but many, scattered across different parts of the sky, you might begin to notice something. They don't all behave exactly the same. At first glance, a supernova seems like a single kind of event. A star brightens suddenly, reaches a peak, and then fades. That pattern is consistent enough that it's easy to think of all supernovae as variations of the same thing. But when astronomers started studying them more carefully, measuring their brightness over time, analysing their light, comparing one event to another, it became clear that there are differences, important ones. Some supernovae reach a very specific brightness, almost like a standard level. Others vary more widely, some fade quickly, others more slowly. Some show clear signs of hydrogen in their outer layers, while others do not. And those differences are not random. They reflect the underlying cause of the explosion. Because while the outward appearance, a sudden brightening, might be similar, the processes that lead to that moment can follow different paths. So instead of a single type of supernova, there are several categories, each with its own story, each with its own way of reaching that final visible event. Now, rather than thinking of these as completely separate phenomena, it helps to think of them as different endings to different kinds of stars. The first broad distinction is based on what we see in the light. When astronomers break down the light from a supernova into its component wavelengths, they can look for specific signatures, lines that indicate the presence of certain elements. One of the most important of these is hydrogen. Some supernovae show clear hydrogen lines in their spectra, others do not, and this simple difference becomes the basis for the first level of classification. Those that show hydrogen are grouped into what is called type 2. Those that do not are grouped into type 1. Now that might sound like a technical detail, but it actually tells us something fundamental about the star that exploded. A type 2 supernova, one that shows hydrogen, comes from a massive star that still has its outer layers intact. Hydrogen is the most abundant element in the universe, and in a typical massive star it forms the outer envelope. So when that star explodes, the hydrogen is still present, and it shows up clearly in the light we observe. A type 1 supernova, on the other hand, lacks those hydrogen lines, which means the outer hydrogen layer is either gone or was never part of the system in the same way. And that immediately suggests a different kind of origin. But even within these broad categories, there are further distinctions. Type 1 supernovae, for example, are not all the same. There is a specific subtype known as type 1a, which behaves in a remarkably consistent way. These supernovae reach nearly the same peak brightness every time, which makes them extremely useful as what astronomers call standard candles. That term doesn't mean they are literal candles, of course, but rather that their brightness is predictable. And if you know how bright something truly is, you can compare that to how bright it appears and determine how far away it is. So type 1, a supernovae have become one of the key tools for measuring distances across the universe. But what makes them so consistent? The answer lies in how they form. Unlike the massive stars we've been talking about so far, which collapse under their own gravity, type 1a supernovae involve a different kind of star entirely, a white dwarf. A white dwarf is the remnant of a smaller star, one that has already gone through its life cycle and shed its outer layers, leaving behind a dense core. On its own, a white dwarf is stable. It no longer undergoes fusion, but it is supported by electron degeneracy pressure, a quantum mechanical effect that prevents it from collapsing further. However, if that white dwarf is part of a binary system, meaning it has a companion star, things can change. If the two stars are close enough, the white dwarf can begin to pull material from its companion. Slowly, steadily, matter accumulates on the surface of the white dwarf, and as that mass increases, the pressure and temperature in the core rise. There is a limit to how much mass a white dwarf can support. This is known as the Chandrasekhar limit, about 1.4 times the mass of the Sun. Once the white dwarf approaches this limit, it becomes unstable, and instead of collapsing in the way a massive star does, it undergoes a runaway fusion reaction. Carbon and oxygen in the white dwarf ignite almost simultaneously throughout the star, and because the star is already dense and degenerate, the usual mechanisms that regulate fusion do not apply. The reaction runs out of control. In a matter of seconds, the entire star is consumed. The result is a thermonuclear explosion. The white dwarf is completely destroyed. No core remains. And because this process happens at a very specific mass threshold, the energy released is very consistent, which is why type 1a supernovae have such predictable brightness. Now, returning to type 2 supernovae, these are the ones more directly connected to the story we've been following. Massive stars, core collapse, shock waves. In these cases, the presence of hydrogen in the outer layers tells us that the star retained its envelope up until the moment of explosion. But even within Type 2, there are variations. Some have light curves that show a plateau, where the brightness remains relatively steady for a period before declining. Others decline more quickly. These differences reflect variations in the structure of the star and the details of the explosion. There are also related categories, Type 1b and Type 1c, which are somewhat in between Type 1 and Type 2. These are also core collapse supernovae, meaning they come from massive stars, but the outer layers of those stars have been stripped away before the explosion. In Type 1b, the hydrogen layer is gone, but helium is still present. In Type 1c, both hydrogen and helium are missing. This stripping can happen due to strong stellar winds or interactions with a companion star that removes the outer layers over time. So even though the core collapse mechanism is similar, the appearance of the supernova differs depending on what layers remain. And that difference shows up in the light. So when astronomers observe a supernova, they are not just seeing an explosion, they are seeing clues about what kind of star it was, what it was made of, how it lived, and how it reached that final moment. It's a bit like looking at the aftermath of an event and working backward to understand what led to it. And because we can observe many supernovae across the universe, we can compare them, classify them, and build a broader understanding of how stars end their lives. But despite these differences, there is something that unites all supernovae. They all involve a sudden release of energy on a massive scale. They all mark the end of a star's life in one form or another, and they all contribute material back into the surrounding space. So while the paths leading to the moment may differ, the outcome shares a common theme: transformation. A star that once existed as a stable, long-lived object becomes something else entirely, either a compact remnant like a neutron star or black hole, or, in the case of a Type 1a, nothing at all, just an expanding cloud of debris. And that cloud, carrying the elements formed during the star's life and its explosion, becomes part of the larger environment, part of the material that will eventually form new stars, new planets, and other structures. So even though the details vary, even though there are different types and subtypes, the role of supernovae in the universe remains consistent. They are endings, but also beginnings. At first, nothing about it looks unusual. There is no massive star nearing the end of its life, no swollen red giant trembling under its own weight, no visible sign of instability. Instead, what you have is something much quieter, a small, dense remnant of a star that has already lived through its dramatic phases and settled into what should have been a stable existence. A white dwarf. On its own, a white dwarf is not particularly eventful. It no longer produces energy through fusion. It simply exists, slowly cooling over time, supported by a kind of pressure that does not rely on temperature or ongoing reactions. Electron degeneracy pressure. That might sound technical, but the idea behind it is simple. The particles inside the white dwarf are packed so closely together that the rules of quantum mechanics prevent them from being squeezed any further without a significant increase in energy. This creates a resistance to compression that holds the star up against gravity. So in isolation, a white dwarf can persist for an incredibly long time. Quiet, stable, unchanging, at least in any noticeable way. But not all white dwarfs are alone. Some exist in binary systems paired with another star, and in those systems the calm, uneventful existence of a white dwarf can begin to change in a way that is almost impossible to notice at first. Because the change does not come from within, it comes from its companion. Imagine two stars orbiting each other. One is a white dwarf, small but extremely dense. The other is a more ordinary star, perhaps still in its main phase of burning hydrogen, or maybe already evolving into a larger, more extended form. If the distance between them is just right, something subtle begins to happen. The white dwarf starts to pull material from its companion, not in a dramatic visible stream at first, more like a gradual transfer. gas from the outer layers of the companion star drifts toward the white dwarf, drawn by its strong gravitational field. And that material does not simply bounce away, it accumulates. Layer by layer, it settles onto the surface of the white dwarf. This process can take a long time, thousands of years, millions even. From the outside, there is no sudden change. The system might glow a bit differently, perhaps emitting X-rays or showing signs of accretion if you look closely with instruments, but to a casual observer, it remains just another point of light in the sky. And yet, something important is happening. The mass of the white dwarf is increasing, slowly, steadily. Every bit of material it gains adds to the total. And here is where things become critical. Unlike a normal star, the white dwarf does not expand easily when its internal conditions change. In a regular star, if the core heats up, the star can expand, relieving some of that pressure and stabilizing the system. But a white dwarf behaves differently. Because of electron degeneracy pressure, its structure does not respond to temperature in the same way. Heating it does not cause it to expand significantly. So as more material accumulates, the pressure and temperature inside the white dwarf rise. But the star does not adjust its size to compensate. It just gets denser, hotter, more tightly packed. And all of this is happening without any outward sign of instability. No swelling, no flickering, no obvious warning. Which is why this kind of supernova is often described as quiet, at least in its build-up. Because everything that matters is happening beneath the surface, hidden, gradual and persistent. Now, there is a limit to how much mass a white dwarf can support. This limit is not arbitrary, it comes from the physics of how electron degeneracy pressure works. At around 1.4 times the mass of the Sun, something known as the Chandrasekhar limit, the pressure from the electrons is no longer enough to support the star against gravity. As the white dwarf approaches this limit, conditions in its interior become extreme. The temperature rises, the density increases, and at some point the conditions become suitable for a new kind of reaction. Carbon fusion. The white dwarf is composed mostly of carbon and oxygen, the remnants of earlier fusion processes from its original star. Under normal conditions, this material is stable, but as pressure and temperature rise, the carbon can begin to fuse. And this is where the situation changes dramatically, because unlike the controlled fusion in a normal star where the system can regulate itself, the white dwarf cannot adjust. There is no expansion to relieve the pressure, no mechanism to slow the reaction. So when carbon fusion begins, it does not proceed gently, it runs away. A runaway reaction is exactly what it sounds like. The fusion process releases energy, which raises the temperature, which increases the rate of fusion, which releases more energy, and so on. It accelerates rapidly. In a matter of seconds, the reaction spreads through the star. The entire white dwarf becomes involved. And because the star is already so dense, the energy released is enormous. This is not a collapse followed by a rebound, as in the core collapse supernovae we discussed earlier. This is a thermonuclear explosion. The star is essentially consumed from within. Carbon and oxygen fuse into heavier elements, releasing vast amounts of energy in the process. The structure of the white dwarf cannot contain this energy, and it is blown apart completely. There is no core left behind, no neutron star, no black hole. The white dwarf is destroyed. All of its material is ejected into space, expanding outward at high speeds. And because this process begins when the star reaches a very specific mass, the amount of energy released is remarkably consistent from one event to another. This consistency is what makes Type 1a supernovae so useful to astronomers. They act like standard markers. If you know how bright something truly is, and you measure how bright it appears, you can determine how far away it is. So Type 1a supernovae have become one of the key tools for measuring the scale of the universe. They've been used to map distances between galaxies, to study the expansion of the universe, even to discover that the expansion is accelerating a finding that led to the concept of dark energy. But stepping back from the measurements and the data, there is something else to notice about this type of explosion. It happens without the long visible warning signs we saw in massive stars. There is no dramatic swelling into a red giant right before the explosion, no series of increasingly rapid fusion stages that lead to a sudden collapse. Instead, there is a quiet build-up, a gradual accumulation of mass, a slow increase in pressure and temperature, and then, almost without warning, a sudden, complete destruction. From the outside, the change is abrupt. A star that seemed stable becomes one of the brightest objects in the sky, and then, over time, it fades, leaving behind no central remnant, only an expanding cloud of debris. And that debris, like in other types of supernovae, carries with it the elements created during the explosion. Those elements spread out into the surrounding space, becoming part of the interstellar medium, the material from which new stars and planets will eventually form. So even though the path to this explosion is different, the outcome shares something with the others: transformation. A quiet system, evolving over long periods, reaches a critical point, and when it does, it changes suddenly, completely, and irreversibly. Out in the darker regions of a galaxy, far from any particular point of attention, there are stars that live very different lives from the quiet white dwarfs we just considered. These are the massive ones, stars that began with far more material, far stronger gravity, and far more intense conditions in their cores. From the very beginning, their story is shaped by that mass. It determines how fast they burn, how bright they shine, and how quickly they move through the stages of their life. And it also determines how they end. Because unlike the silent buildup of a white dwarf in a binary system, the path toward a Type II supernova is something that unfolds entirely within a single star. No companion required. No external trigger. Just the internal processes of a star that has been burning through its fuel at a remarkable pace since the moment it formed. If you could follow one of these stars from its early life, you would notice something almost immediately. It is brighter than most. Not just a little brighter, but significantly so. Massive stars can shine tens of thousands, even millions of times more brightly than the sun. That brightness is a direct result of how quickly they are burning their fuel. High mass leads to strong gravity. Strong gravity leads to higher pressure in the core. Higher pressure leads to higher temperatures, and higher temperatures accelerate fusion. So instead of settling into a slow, steady burn that lasts for billions of years, these stars burn intensely. They move quickly through their fuel, progressing from one stage of fusion to the next in a way that is both efficient and short-lived. Their lives, while still long by human standards, are brief compared to smaller stars. Millions of years instead of billions. And during that time, they build something important, a layered core. As hydrogen is fused into helium and helium into heavier elements, the core becomes more complex. Different fusion processes occur at different depths, creating shells where specific elements are formed. Hydrogen fuses in one region, helium in another. Carbon, oxygen, neon, silicon, each in their own layer. Over time, this creates a structure that resembles a set of nested shells, each one contributing to the overall balance of the star. And for a while, this works. The star maintains its structure, continues to shine, continues to evolve. But as we've already begun to see, this process cannot continue indefinitely. Each stage of fusion becomes less efficient at producing the outward pressure needed to counteract gravity. And eventually, the star reaches a stage where its core is dominated by iron. And iron, as we've said before, does not help the star in the way earlier elements did. Fusing iron does not release energy. It absorbs it. So once the core is filled with iron, the star loses its ability to generate the outward pressure that has supported it for so long. And at that point, the balance breaks. Gravity takes over, the core collapses. This is the beginning of the core collapse process that leads to a Type II supernova. Now, unlike the Type 1a case, where the entire star is consumed in a thermonuclear explosion, here the story is a bit different. The collapse is focused on the core. The outer layers are still present, still intact, and they play a crucial role in what happens next. As the core collapses, it reaches extreme densities and temperatures. Electrons are forced into protons, forming neutrons. Neutrinos are produced in vast numbers. The inner core stiffens due to neutron degeneracy pressure. And then, as we've already explored, the collapse halts and rebounds. A shockwave forms. That shockwave begins to move outward, and this is where the outer layers come into play. Because those layers, still rich in hydrogen, are now struck by the shockwave. They are heated, compressed, accelerated outward, and as they expand, they carry with them the signature of hydrogen, which is why Type 2 supernovae show hydrogen lines in their spectra. This is one of the defining features of this type of explosion. The presence of hydrogen tells us that the star retained its outer envelope up until the moment of collapse. It did not lose it to strong winds or interactions with a companion. It held onto it, and when the explosion occurred, that envelope was expelled along with everything else. Now, there are variations within Type 2 supernovae. Some show a plateau in their brightness over time, where the light remains relatively steady for a period before fading. These are often referred to as Type 2p. Others show a more gradual decline in brightness without a plateau, known as Type 2l. These differences are related to the structure of the star and how its outer layers respond to the explosion. But the underlying mechanism remains the same: core collapse, shockwave, explosion. And unlike Type 1a supernovae, which leave no remnant, Type 2 supernovae almost always leave something behind. The core that collapsed does not disappear. It becomes something new. If the remaining mass is within a certain range, it forms a neutron star, an incredibly dense object where matter is packed to such an extent that a small amount would weigh more than entire mountains on Earth. If the mass is even greater, the collapse continues beyond that point, forming a black hole. So in this type of supernova, the star does not vanish completely. Part of it remains, a compact remnant at the centre of an expanding cloud of debris. And that debris, like in other supernova, spreads out into space, carrying with it the elements that were formed during the star's life and in the explosion itself. These elements mix with the surrounding gas and dust, becoming part of the material that will eventually form new stars, new planets, and other structures. So while the explosion marks the end of the star's life, it also contributes to the ongoing evolution of the galaxy. Now, there is something else to notice about Type 2 supernovae. They are not rare in the grand scheme of the universe. Massive stars are less common than smaller ones, but when they do form, they evolve quickly, which means that on a cosmic timescale, these explosions happen regularly. Somewhere in the universe, at almost any given moment, a massive star is reaching the end of its life and undergoing this process, and each of those events adds to the overall cycle. Stars form from clouds of gas and dust. They live, they evolve, they die, and in doing so they return material to the environment, enriched with heavier elements. That material then becomes the building blocks for the next generation of stars. So when we look at a Type 2 supernova, we are not just looking at an isolated event. We are looking at a step in a much larger cycle. A cycle that has been ongoing for billions of years, a cycle that shapes the composition of galaxies, and a cycle that ultimately makes the existence of complex matter and life possible. Because without these explosions, many of the elements we rely on would not exist in the form we know. They would remain locked inside stars, never released into the wider universe. So even though the death of a massive star is a dramatic event, it is also a necessary one, a process that transforms and redistributes matter. What's left behind does not always vanish. After everything we've followed, the long life, the slipping balance, the collapse, the rebound, and the outward explosion, it might seem like the story ends with the star tearing itself apart completely. And in some cases that's true, but not here. In many of these massive star endings, something remains at the centre. Something that has gone through the collapse and survived it. Though survived might not be the right word, because what emerges is no longer anything like the star that existed before. It is smaller, far smaller, and yet, in a different sense, far more extreme, a neutron star. Now, to understand what that really means, it helps to step back for a moment and consider what happened during the collapse. As the core of the star fell inward, matter was compressed to extraordinary densities. Atoms were broken apart, electrons were forced into protons, neutrons formed in vast numbers. The familiar structure of matter, atoms with empty space and orbiting electrons, no longer existed in the same way. Everything was packed together. And when the collapse was finally halted, when neutron degeneracy pressure took over and stopped further compression, what remained was this dense core made mostly of neutrons. That core is the neutron star, and it is unlike anything we encounter in everyday experience. To get a sense of it, imagine taking a mass greater than that of the Sun and compressing it into a sphere only about 20 kilometers across. That's roughly the size of a city. All that mass, all that material, packed into something so small that compared to the original star, it almost disappears. But it doesn't disappear. It becomes something incredibly dense. The density is so high that a single teaspoon of neutron star material would weigh billions of tons on Earth. Not because the material itself is somehow heavier in the usual sense, but because so much mass is concentrated into such a small volume. There is almost no empty space left. The particles are as close together as they can be without collapsing further, and even at that extreme density there is still structure. The outer layers of a neutron star form a kind of crust, made of tightly packed nuclei and electrons. Beneath that, the matter becomes even more compressed, forming a fluid of neutrons that behave in ways that are still being studied and not fully understood. It is a state of matter that does not exist naturally anywhere else we can observe directly. And yet, this is the remnant left behind after a supernova. Now, one of the most noticeable properties of a neutron star is its gravity. Even though it is small in size, its mass is enormous. That means the gravitational pull at its surface is extremely strong. If you were somehow able to stand on the surface, which is not possible in any practical sense, the gravity would be so intense that it would flatten anything we recognize as matter. But the effects of that gravity extend beyond just the surface. The space around the neutron star is affected. Light passing near it is bent. Time itself is slightly altered, running more slowly in the strong gravitational field compared to farther away. These effects are predicted by general relativity, and neutron stars are one of the places where those predictions can be tested. But there is something else about neutron stars that stands out even more: rotation. When the core of the star collapses, it does not lose its rotation. In fact, because the size decreases so dramatically, the rotation speeds up. It's similar to how a figure skater spins faster when they pull their arms in. The original star might have rotated slowly, but as the core collapses into a much smaller object, that rotation becomes much faster. So neutron stars can spin incredibly quickly. Some rotate several times per second. Others, known as millisecond pulsars, can rotate hundreds of times per second. And when they do, they can produce beams of radiation that sweep through space. If one of those beams happens to point toward Earth as the neutron star rotates, we detect it as a regular pulse of radiation. This is where the term pulsar comes from. A pulsating star, though again not in the sense of expanding and contracting, but in the sense of emitting regular pulses of energy as it spins. These pulses are incredibly precise. So precise, in fact, that pulses can be used as cosmic clocks, measuring time with remarkable accuracy. And this regularity is a direct result of the stability of the neutron star's rotation. Even after the violence of the supernova, the remnant settles into a consistent pattern. It spins, it emits radiation, it continues in its own way, long after the original star is gone. Now, not all neutron stars become pulsars that we can detect. Some do not have the right alignment for their radiation beams to be visible from Earth. Others may not produce strong enough emissions in the wavelengths we observe, but the underlying object is the same, a dense, compact remnant. Now, it's also worth considering how stable a neutron star is. After everything it has been through, the collapse, the rebound, the explosion, it might seem like it would be unstable, prone to further changes. But in many cases, neutron stars are quite stable. They can persist for millions or billions of years, slowly cooling over time, gradually losing energy, but maintaining their structure. However, there are limits. If the mass of the core is too great, even neutron degeneracy pressure is not enough to stop the collapse. In that case, the neutron star does not form, or it forms only briefly before collapsing further into a black hole. But when the mass is within the right range, the neutron star remains, a lasting remnant of the explosion. And around it, the material that was ejected during the supernova continues to expand. That material interacts with the surrounding space, forming structures known as supernova remnants, clouds of gas and dust enriched with heavy elements, expanding outward over thousands of years. The neutron star sits at the center of this expanding cloud, a small, dense point within a much larger evolving structure. And this relationship is important, because while the explosion disperses material into space, the neutron star remains as a kind of anchor point, a reminder of what was once there, a trace of the original star, but not in its original form, completely transformed. There is a point beyond which even the most extreme forms of resistance no longer matter. Up until now, every stage we've followed has involved some kind of balance, even if that balance was temporary. Fusion held stars up for most of their lives. Electron degeneracy pressure supported white dwarfs. Neutron degeneracy pressure halted the collapse of many massive cores and gave rise to neutron stars. Each time gravity pushed inward, something eventually pushed back. But that pattern does not continue forever, because there are cases where the mass of the collapsing core is simply too great, too much matter, too much gravity, and in those cases even the dense, tightly packed neutrons cannot provide enough resistance to stop the inward pull. So instead of halting, the collapse continues, and this is where the story changes in a way that is difficult to visualize, because the outcome is not something we can observe directly in the usual sense. The core keeps collapsing. There is no rebound, no shock wave created by a sudden halt, no stable surface where pressure balances gravity. Just continued inward motion, faster, denser, more extreme. Now, at first this might sound like an extension of what we've already described, a more intense version of the same process, but it's not simply a matter of degree, it's a change in kind, because as the collapse continues, the conditions reach a point where the concepts we've been using to describe matter begin to break down. The particles are forced closer together than they have ever been. The density increases beyond what neutron degeneracy pressure can support, and gravity becomes so strong that it begins to dominate not just matter, but space itself. This leads to the formation of a black hole. Now that term, black hole, is often associated with something mysterious, something almost abstract. But at its core, it describes a very specific situation, a region of space where gravity is so strong that nothing can escape from it, not even light. To understand what that means, it helps to think about escape velocity. On Earth, if you throw something upward, it falls back down because gravity pulls it back. But if you could throw it fast enough, at about 11 kilometers per second, it would escape Earth's gravity entirely. That's escape velocity. For more massive objects, the escape velocity is higher. For a neutron star, it's already extremely high. But for a black hole, the escape velocity exceeds the speed of light. And since nothing can travel faster than light, nothing can escape. Not particles, not radiation, not even information. Everything that crosses a certain boundary is trapped. That boundary is known as the event horizon. It's not a physical surface you can touch. It's more like a point of no return. Once something passes inside it, there is no path that leads back out. Now, here's where things become even more interesting. From the outside, the formation of a black hole might not look dramatically different at first from the formation of a neutron star. The star collapses. A shock wave may still be produced, driving the outer layers outward. A supernova can still occur, but at the centre, instead of a neutron star forming and remaining stable, the collapse continues. And as it continues, the region that will become the black hole shrinks to an incredibly small size. At least according to the simplest models, it shrinks towards something called a singularity, a point where density becomes infinite, and the known laws of physics can no longer describe what is happening. Now, it's important to be careful with that idea. Singularities are not something we fully understand. They represent a limit in our current theories, a place where general relativity, our best description of gravity, and quantum mechanics, our best description of small-scale physics, do not yet fit together in a complete way. So while the mathematics suggests a singularity, the true nature of what exists at the centre of a black hole is still an open question. But even without knowing the details of the centre, we can understand the structure around it. The event horizon marks the boundary. Outside it, the gravitational effects are strong, but still follow known laws. Inside it, everything moves inward. There are no stable orbits, no way to remain at a fixed distance. Everything is drawn toward the centre. Now, from the perspective of an observer far away, something unusual happens. If you were watching an object fall toward a black hole, it would appear to slow down as it approaches the event horizon. Its light would become stretched, red-shifted, and dimmer. It would never quite seem to cross the boundary. Instead, it would fade away, becoming less and less visible. But from the perspective of the object itself, the experience is different. It would cross the event horizon in a finite amount of time, without noticing anything particularly special at that exact boundary. The point of no return is not marked by a sudden change in local conditions. It's defined by what paths through space-time are possible afterward. Once inside, all paths lead inward. Now, in the context of a supernova, what this means is that the core of the star collapses beyond the neutron star stage and becomes a black hole. The outer layers are still expelled. The explosion still spreads material into space, but at the centre there is no solid remnant, no surface, no stable object in the usual sense. There is a region from which nothing escapes, and yet, even though we cannot see inside a black hole, we can observe its effects. Material that falls toward it can form an accretion disk, a swirling structure of gas that heats up as it spirals inward. That gas can emit radiation, sometimes very strongly, making the region around a black hole one of the brightest sources of energy in the universe. So while the black hole itself is dark, the environment around it can be anything but. But in the immediate aftermath of a supernova, the black hole is simply the end point of the collapse, the inward motion that never stopped, the continuation of gravity's dominance beyond all forms of resistance. And in that sense, it represents a different kind of ending. Where a neutron star is a compressed remnant, still made of matter in a recognizable form, a black hole is something more extreme, a transformation not just of matter, but of the structure of space and time in that region. And this raises an interesting point. Throughout this entire process, from the life of the star to its collapse and explosion, gravity has been a constant presence. It shaped the star's formation. It balanced fusion during its life. It drove the collapse at the end. And in the case of a black hole, it continues to act without limit. There is no opposing force left, no equilibrium to restore, only continued inward pull. It becomes clear that whether the core becomes a neutron star or a black hole, the explosion itself plays a larger role beyond the fate of the remnant. Because the material that is expelled, the elements that are created and the energy that is released all contribute to the environment around the star. Long before any explosion, long before the shock wave and the sudden brightening, something much quieter has already been happening inside the star. For most of its life, the star has been changing what it is made of. Not in a dramatic way from the outside, not in a way you could ever see just by looking at it in the sky, but steadily, consistently, deep in the core where the pressure and temperature are high enough to make it possible. Hydrogen becomes helium, helium becomes carbon, carbon becomes heavier elements, and so on. Each stage builds on the one before it, and by the time the star reaches the end of its life, especially in the case of massive stars, it has created a layered structure of elements that did not exist there at the beginning. But even that is not the full story, because while stars can create many elements during their stable phases, there are limits to what can be produced this way. Fusion works well up to a point. It releases energy when lighter elements combine into heavier ones, but only up to iron. Once iron is reached, the process changes. Fusing iron does not release energy, it consumes it. And that is one of the reasons the collapse begins in the first place. So if fusion stops at iron, where do the heavier elements come from? Gold, silver, uranium, the kinds of elements that are heavier than iron, the ones that require more energy to form than they release. The answer lies in the explosion itself, because the conditions during a supernova are very different from anything that exists during the stable life of a star. When the core collapses and rebounds, when the shock wave moves outward and the outer layers are accelerated, the temperatures and pressures become extreme in a way that is both brief and intense. For a short period of time, the environment inside the exploding star becomes energetic enough to drive reactions that would otherwise be impossible. And one of the key processes that takes place is rapid neutron capture. This is often referred to as the R process. Now, rather than thinking about it in technical terms, it helps to imagine what is happening at a basic level. During the explosion, a large number of neutrons are released. These neutrons move through the surrounding material, interacting with atomic nuclei. And because neutrons do not carry an electric charge, they can be absorbed by nuclei more easily than charged particles. So nuclei that were formed earlier, iron for example, can rapidly capture neutrons. They can gain more and more of them in a very short time. This process happens faster than the nuclei can stabilize themselves through normal decay, so they become heavier and heavier, moving beyond the usual limits of stable elements. And then, after the explosion has passed and conditions begin to calm, these neutron-rich nuclei undergo radioactive decay. They transform into more stable forms, often becoming entirely new elements in the process. This is how many of the heavy elements are formed, not during the long, steady life of the star, but in the brief, intense moments of the explosion. And those elements do not remain in the star, because the star is no longer holding itself together. The explosion has already begun to push material outward. So as these elements are formed, they are carried along with the expanding cloud of debris. They are ejected into space. Now this is where the story begins to extend beyond the star itself, because once those elements are released, they become part of the surrounding environment. They mix with the gas and dust that already exist in the galaxy. They spread out over time, carried by the motion of the expanding remnant and by interactions with other material, and eventually they become part of something new. New stars, new planetary systems, new structures that form from the enriched material. So when we talk about the elements that come from explosions, we're not just talking about a byproduct of the supernova. We're talking about a process that contributes directly to the composition of the universe as a whole. Before the first generations of stars, the universe was made mostly of hydrogen and helium. Those were the simplest elements, formed in the early moments after the Big Bang. But the heavier elements, the ones that make up planets, that form solid structures, that are part of biological systems, those came later. They were built in stars, and then released through events like supernovae. So in a very real sense, the explosion of a star is not just an ending. It is also a distribution event, a way of taking the products of stellar evolution and spreading them out into space. Now, it's worth considering how much material is involved. A massive star contains a huge amount of matter. When it explodes, a significant portion of that matter is expelled. Not all of it, Some remains in the form of a neutron star or a black hole, but a large fraction is sent outward. And within that material are all the elements that were formed during the star's life and during the explosion itself. These elements are not evenly distributed. The explosion is complex. Some regions may be richer in certain elements than others. There can be mixing, turbulence, and variations in how the material is ejected. But over time, as the remnant expands and interacts with the surrounding space, those differences begin to even out. The elements spread. They become part of the interstellar medium, and over very long periods they are incorporated into new structures. Now, bringing this closer to something more familiar, it's worth noting that many of the elements we encounter in everyday life were formed in these kinds of events. The iron in tools and buildings, the calcium in bones, the gold in jewellery. These elements were not present in the early universe in the form we use them. They were created in stars and distributed through explosions. So when we talk about supernovae producing elements, we are not talking about something abstract or distant in a purely theoretical sense. We are talking about processes that have directly contributed to the material that makes up our world. But even without focusing on that connection, there is something interesting about the timing. For millions of years, the star builds up these elements in its core, slowly, layer by layer. Then, in a matter of seconds, the explosion occurs, and in those seconds new elements are created and everything is ejected outward. A long period of accumulation followed by a brief moment of release, and that pattern repeats across the universe. Stars form, they evolve, they produce elements, they explode, and the material is redistributed. It is a cycle, not a simple one, not a perfectly repeating one, but a cycle nonetheless, and each supernova contributes to that cycle, adding more material, more complexity, more variety to the composition of the universe. Now, as we continue to follow what happens after the explosion, the focus shifts even further outward, because the material that has been ejected does not remain static. It continues to move, to expand, to interact with the surrounding environment, and over time, it forms structures that can be observed long after the initial brightness of the supernova has faded. Clouds of gas and dust that carry the imprint of the explosion. Structures that reveal how the shockwave moved, how the material was distributed, and how the elements were mixed. Galaxies might look calm from a distance. If you picture one, you probably imagine a smooth spiral of light, or a soft glowing cloud filled with countless stars, all arranged in a way that feels almost still. There's no obvious motion, no sign of disruption, just a quiet structure suspended in space. But that calm appearance hides something much more active, because galaxies are not static. They are constantly changing, constantly evolving, and a large part of that change comes from events that happen on a much smaller scale, the life and death of individual stars. And among those events, supernovae play a particularly important role, not because they happen everywhere all the time, but because when they do happen, they release enough energy and material to influence their surroundings in ways that extend far beyond the star itself. To understand how this works, it helps to think about what a galaxy is made of. It's not just stars. There is also gas and dust spread throughout the space between them. This material, known as the interstellar medium, is not evenly distributed. It forms clouds, filaments, and regions of varying density. Some of these regions are relatively empty. Others are dense enough that gravity can pull them together to form new stars. So a galaxy is not just a collection of stars, it is also a reservoir of material from which new stars can form. And this is where supernovae come in. When a star explodes, it does more than just release light. It sends out a shockwave. That shockwave moves through the surrounding interstellar medium, pushing against the gas and dust it encounters. And when it does, it can have several effects. One of the most immediate is compression. As the shockwave travels outward, it compresses the gas in front of it. Regions that were previously diffuse can become denser, and when gas becomes dense enough, gravity can take over, pulling that material together to form new stars. So in this way, a supernova can trigger star formation. Not directly, not by creating stars itself, but by altering the conditions in the surrounding environment so that star formation becomes more likely. It's a bit like pushing together a cloud of material until it reaches the point where it can collapse under its own gravity, and this process can happen over large distances. The shock wave from a supernova can travel for many light years, affecting regions far beyond the original star. But that's only one side of the story, because the same shock wave that compresses some regions can also disperse others. If the gas is not dense enough to resist the pressure of the shock wave, it can be pushed apart, spreading out into space and becoming less likely to form stars. So supernovae can both encourage and inhibit star formation, depending on the conditions. They can create new stars in some regions while preventing them in others. And over time, this balance of effects helps shape the overall structure of the galaxy. Now, there is another aspect to consider. The material that is ejected during a supernova is not the same as the material that was present before. As we discussed earlier, the explosion produces heavy elements. These elements are mixed into the interstellar medium as the debris expands. So the gas and dust that fill a galaxy are gradually enriched with these heavier elements over time. This enrichment has important consequences, because the composition of the gas affects how stars and planets form. In the early universe, before many generations of stars had lived and died, the material available for star formation was mostly hydrogen and helium. Stars formed from that material were different from the ones we see today, but as supernovae occurred, they added heavier elements to the mix, and with each generation of stars, the overall composition of the galaxy changed. This process is sometimes referred to as chemical evolution, not in the sense of biology, but in the sense of increasing complexity in the types of elements present. And supernovae are one of the main drivers of that process. They take elements that were locked inside stars and release them into the wider environment. Over time, this leads to a galaxy that is richer in heavy elements, which in turn affects the kinds of structures that can form. Planets, for example, require heavy elements. Solid materials like rock and metal cannot form from hydrogen and helium alone. So without supernovae, the formation of planets like Earth would not be possible in the same way. But beyond the creation of elements and the triggering of star formation, supernovae also contribute energy to the galaxy. A lot of energy. When a supernova explodes, it releases energy not just in the form of light, but also in the motion of the ejected material. That material moves outward at high speeds, carrying kinetic energy into the surrounding space. As it interacts with the interstellar medium, it transfers that energy to the gas. This can heat the gas, increase its motion, and create turbulence. And this turbulence can affect how gas clouds evolve. In some cases, it can support them against collapse, delaying star formation. In others, it can help mix different regions of the galaxy, distributing elements more evenly. So the energy from supernovae contributes to the overall dynamics of the galaxy. It helps keep the interstellar medium from settling into a completely uniform state. It maintains a level of activity, of motion, of change. Now, if you consider a galaxy over long periods of time, billions of years, these effects add up. Supernovae occur repeatedly, not in the same place, not at the same time, but throughout the galaxy. Each one contributes a small part to the overall evolution, and together they shape the structure and behavior of the galaxy. They influence where stars form. They determine how elements are distributed. They affect the motion and temperature of the gas. So while a single supernova is a localized event, its impact extends outward. And when many such events are considered together, they become a significant factor in how galaxies evolve. It's also worth noting that the rate of supernovae can vary between galaxies. Galaxies with higher rates of star formation tend to have more massive stars, and therefore more core collapse supernovae. Galaxies with older stellar populations may have more Type 1a supernovae, as white dwarfs in binary systems reach the conditions needed for explosion. So the type and frequency of supernovae can tell us something about the history and current state of a galaxy. They are not just events, they're indicators, clues about what is happening on a larger scale. And as we continue to observe galaxies across the universe, we see that supernovae are a common part of their life cycles. Not constant, not overwhelming, but present enough to matter. Present enough to shape the environment in meaningful ways. Now, bringing this back to the individual star, it becomes clear that the explosion is not just the end of that star's story. It is a contribution to something larger. The material it releases becomes part of the galaxy. The energy it injects influences the surrounding gas, and the effects of that explosion can persist long after the initial light has faded. So when we think about supernovae shaping galaxies, we are really thinking about a network of interactions between stars and gas, between energy and structure, between individual events and long-term evolution. Out of everything we've explored so far, this is the point where the question becomes a little more personal. Up until now, the story has unfolded at a distance. Massive stars living out their lives far away, collapsing, exploding, reshaping their surroundings, all of it happening on scales so large that it feels almost separate from anything we experience directly. But it's natural to wonder, could any of this ever affect us? Could a supernova, something so powerful, have consequences for Earth? The short answer is yes, but the longer answer, the one that really matters, depends entirely on distance. Because space is vast, and that distance changes everything. When a star goes supernova, it releases an enormous amount of energy. Light, radiation, fast-moving particles, all of it spreads outward in every direction, but as that energy travels, it spreads out over a larger and larger area, so by the time it reaches distant regions, it is much less concentrated. This is why most supernovae we observe have no effect on us beyond being visible in the sky. They're simply too far away. Their light reaches us, their story becomes visible, but their energy is diluted across such a vast volume of space that it poses no threat. Now, to understand what would happen if a supernova were closer, it helps to break down the different ways it could affect a planet. The first and most immediate effect would come from radiation. When the explosion occurs, it releases high-energy radiation, including gamma rays and X-rays. These forms of radiation carry a lot of energy, and if a planet is close enough, they can interact with its atmosphere in significant ways. For Earth, the atmosphere acts as a shield. It absorbs much of the incoming radiation, protecting life at the surface. But if the radiation is intense enough, it can begin to alter the atmosphere itself. One of the main concerns is the ozone layer. The ozone layer protects the surface from harmful ultraviolet radiation from the sun. If a nearby supernova were to disrupt or deplete that layer, more UV radiation could reach the surface. This would not be an immediate dramatic event like something being destroyed in an instant. It would be more gradual, an increase in radiation levels, potential damage to ecosystems, changes that unfold over time rather than in a single moment. Another effect comes from cosmic rays. These are high-energy particles that are accelerated during the explosion and in the shockwave that follows. They travel through space and can reach planets long after the initial light from the supernova has arrived. Cosmic rays can interact with the atmosphere as well, producing secondary particles and contributing to changes in atmospheric chemistry. They can also reach the surface, although again, the atmosphere provides significant protection. Still, if the flux of cosmic rays is high enough, it could have biological effects. Now there is also the possibility of a more direct effect if the supernova is extremely close. At very short distances, the energy released could be strong enough to have more immediate consequences, heating the atmosphere, increasing radiation levels significantly, and potentially causing widespread disruption. But this requires a very close event, on the order of a few tens of light years, and this is where probability becomes important. Because while supernovae do occur regularly across the universe, the chances of one happening that close to Earth are very low. Most of the stars near us are not massive enough to go supernova. Massive stars are relatively rare, and they tend to exist in regions of active star formation, which are often located in different parts of the galaxy. So while it is possible in principle, it is not something that happens frequently on timescales relevant to human history. Now, there is some evidence that supernovae may have affected Earth in the distant past. Scientists have found traces of certain isotopes, like iron-60, in ocean sediments and lunar samples. These isotopes are produced in supernovae and have relatively short half-lives, which means they must have been deposited relatively recently in geological terms. This suggests that supernovae have occurred close enough to Earth in the past to leave detectable signatures, but even in those cases the effects do not appear to have been catastrophic. They may have influenced the environment in subtle ways, possibly contributing to changes in climate or biological systems, but not in a way that led to immediate widespread destruction. So the idea of a supernova affecting Earth is not purely hypothetical. It has likely happened in some form before, but the scale of that effect depends strongly on distance. Now, it's also worth considering what we would see if a supernova occurred relatively close, even if it were not close enough to be dangerous. As we discussed earlier, it would appear as a very bright point of light in the sky, possibly visible during the day, casting shadows at night, a constant presence for weeks or months. And while the visual aspect might be striking, the physical effects would likely remain limited if the distance is sufficient. So in most realistic scenarios, the impact on Earth would be minimal, a remarkable sight in the sky, an opportunity for observation, but not a threat. And this brings us back to something important: scale. The energy involved in a supernova is enormous, but space is vast, and that vastness provides a kind of natural buffer. It spreads out the energy, reduces its intensity, and ensures that most events remain distant phenomena. Now, that doesn't mean supernovae are irrelevant to us. Far from it. As we've already seen, they play a crucial role in creating and distributing the elements that make up planets and life. They shape galaxies. They influence star formation. So even if a supernova does not directly affect Earth in a dramatic way, it has still contributed to the conditions that make Earth what it is. And in that sense, the connection is indirect but very real. The elements in our world, the structure of our galaxy, the environment in which our solar system formed, all of these have been influenced by supernovae over time. So while the idea of a nearby explosion might sound concerning at first, the reality is more balanced. Yes, it could have effects, but the chances of a dangerous event are low, and the role of supernovae in the larger picture is one of creation as much as destruction. Look back through human history for long enough, and you begin to notice something interesting about the night sky. It feels permanent. Ancient observers, just like us, looked up and saw patterns that didn't seem to change. The same constellations, the same steady stars, the same sense that the sky was fixed, almost timeless. And for the most part, that impression holds true. Stars do move, but over time scales far longer than a human lifetime, so the sky appears stable, predictable, reliable. Which is exactly why, on the rare occasions when something new appeared, it stood out immediately, not gradually, not subtly, but suddenly. A star where there had been none before, or one that was so faint it had never been noticed, now shining brightly enough to demand attention. These events were recorded carefully, not because people understood what they were seeing in terms of stellar physics, but because the change itself was impossible to ignore. They called them new stars, or sometimes guest stars, and what they were witnessing was supernovae. Now, what makes these historical observations particularly interesting is not just that they exist, but that they give us a direct human connection to events that are otherwise incredibly distant and rare. Because even though supernovae occur regularly across the universe, seeing one with the naked eye within our own galaxy is uncommon. It doesn't happen often within a single lifetime, so when it does, it becomes something that is remembered, something that is written down, something that crosses cultures and generations. One of the earliest well-documented examples comes from the year 1054. observers in China, as well as in other parts of the world, recorded the appearance of a new star in the sky. It was bright enough to be seen during the day for weeks, and at night it was one of the most prominent objects in the sky. They described its position carefully. They tracked how its brightness changed over time, and then, eventually, it faded. What they didn't know at the time was that they had witnessed the death of a massive star. Today, we can look at the same region of the sky and see what remains: the Crab Nebula, a cloud of expanding gas still carrying the imprint of that explosion nearly 1,000 years later. At its centre lies a neutron star, a pulsar, spinning rapidly and emitting regular pulses of radiation. So when we connect the historical record to modern observations, we're able to trace the full arc of that event, from the sudden appearance of light in the sky to the long-lived remnant that continues to evolve. Another famous example comes from 1572. This one was observed by Tycho Brahe, a Danish astronomer who carefully documented the appearance of a new star in the constellation Cassiopeia. What made this observation particularly important was not just the brightness of the object, but the conclusion that followed. At the time, many believed that the heavens were unchanging, that the stars were fixed and eternal. But this new star challenged that idea. Tycho Brahe observed that it showed no parallax, meaning it was not close to Earth. It had to be among the stars, which meant that something in the supposedly unchanging heavens had changed. That realization was significant. It helped shift the understanding of the cosmos from something static to something dynamic, something capable of change. The object itself, now known as Tycho's supernova, has left behind a remnant that can still be studied today. A shell of expanding gas, revealing details about the explosion that occurred centuries ago. Then, a few decades later, in 1604, another supernova appeared. This one was observed by Johannes Kepler and is often referred to as Kepler's supernova. Like the others, it appeared suddenly, brightened, and then faded over time. And like Tycho's observation, it contributed to the growing understanding that the universe is not fixed, that stars can change, that new objects can appear, and that the sky is not as unchanging as it once seemed. Now, since those early observations, we've seen many more supernovae, but most of them are in distant galaxies. With modern telescopes, we can detect supernovae that occur millions or even billions of light years away. They appear as small points of light in distant galaxies, but their brightness and behaviour can still be measured in detail. One particularly notable example in more recent history is SN 1987A. This supernova occurred in the Large Magellanic Cloud, a nearby galaxy that orbits our own. It was close enough, relatively speaking, that it could be studied in unprecedented detail with modern instruments. Astronomers were able to observe not just the light from the explosion, but also neutrinos, those nearly massless particles that were released during the core collapse. This provided direct evidence of the processes happening deep inside the star. For the first time, we were not just seeing the aftermath, we were detecting signals from the core itself, and that marked a significant step forward in our understanding. Now, what's interesting about all of these examples is how similar the human experience of them has been, despite the differences in technology. In ancient times, observers looked up and saw a new star. They recorded its position, they noted its brightness, they watched it fade. Today, we do the same, but with far more detail. We use telescopes to measure its spectrum. We track its light curve precisely. We detect neutrinos and other signals. But the basic experience remains: a sudden change in the sky, a new point of light, and a gradual fading over time. There is something consistent about that, something that connects observers across centuries. Now, it's also worth noting that within our own galaxy, we have not observed a supernova with the naked eye since the early 1600s. That doesn't mean none have occurred. It's possible that some were obscured by dust, or occurred in regions of the galaxy that are not easily visible from Earth. but it does mean that such events are rare on human timescales. So while supernovae are common across the universe, seeing one close enough to be visible without instruments is unusual, and that rarity adds to their significance. When one appears, it becomes an event, something that stands out, something that is remembered. Now, as we continue to observe the universe with more advanced tools, we are discovering supernovae more frequently, not because they are happening more often, but because we are better at detecting them. We can monitor large areas of the sky continuously, we can detect changes quickly, and we can study these events in ways that were not possible before. But even with all of that, the idea of seeing one with your own eyes, without instruments, remains special, because it connects the abstract, distant processes of stellar evolution to something immediate, something visible, a reminder that the universe is not static, that even the stars can change, and that occasionally those changes become visible to us in a very direct way. Before any explosion is even visible, long before a sudden bright point appears in the sky, scientists are already watching, not a single star in isolation, but vast portions of the sky at once. Modern astronomy does not rely on waiting for something dramatic to happen and then reacting to it. Instead, it works more like a continuous survey. Large telescopes scan the sky over and over again, night after night, building up a detailed record of what is there and how it changes. So when a supernova occurs, it is not usually discovered by chance. It is detected as a change, a comparison between what was there before and what is there now, a new point of light, or a familiar one that has suddenly grown brighter. And once that change is detected, the process of studying the explosion begins almost immediately, because supernovae evolve quickly. Their brightness rises, peaks, and then begins to fade, all within a relatively short period of time compared to the life of a star, so timing matters. The sooner the event is identified, the more information can be gathered about its earlier stages. Now, one of the first things scientists do is measure the light. Not just how bright it is, but how that brightness changes over time. This is called a light curve. By tracking the brightness day by day, sometimes even hour by hour in the early stages, scientists can build a detailed picture of how the explosion unfolds. Different types of supernovae have different light curves. Some rise quickly and fade quickly. Others take longer to reach their peak and decline more slowly. Some show plateaus, periods where the brightness remains relatively steady. And these patterns are not random. They reflect the physical processes happening inside the explosion. So by studying the light curve, scientists can begin to classify the supernova and understand what kind of event it is. But brightness alone is not enough. The next step is to analyze the light in more detail. Instead of treating it as a single value, scientists break it into its component wavelengths, a process known as spectroscopy. This reveals patterns, lines that correspond to specific elements. Hydrogen, helium, iron, and many others each leave their signature in the spectrum. And by examining these signatures, scientists can determine what the exploding star was made of. They can see which elements are present, which are absent, and how those elements are moving. Because the lines in the spectrum are not always in the same position, they can be shifted. If the material is moving away from us, the lines shift toward longer wavelengths, what we call redshift. If it is moving toward us, they shift in the opposite direction. So by measuring these shifts, scientists can determine how fast the material is expanding, and in a supernova those speeds are enormous, thousands of kilometers per second, sometimes more. So within just a few observations, scientists can learn a great deal. The type of supernova, the elements involved, the speed of the explosion, but the study does not stop there, because supernovae do not only emit visible light, they also produce radiation across the entire electromagnetic spectrum. X-rays, gamma rays, radio waves. Each of these provides different information. X-rays can reveal high-energy processes in the shock wave and in the interaction between the expanding material and the surrounding gas. Radio waves can show how the shock wave moves through the interstellar medium, how it compresses and heats the gas, and how magnetic fields are involved. Gamma rays can provide information about radioactive decay processes occurring in the ejected material, so scientists use multiple types of telescopes, not just those that detect visible light, but also those designed to observe other wavelengths, and by combining all of this data, they can build a more complete picture of the explosion. Now, there is something else that has become increasingly important in recent years: neutrinos. As we discussed earlier, neutrinos are produced in large numbers during the core collapse of a massive star. They escape almost immediately, passing through the star and through space with very little interaction. Detecting them is extremely difficult, but when it is possible, they provide direct information about what is happening in the core, something that light alone cannot do, because light takes time to escape from the star's outer layers. Neutrinos, on the other hand, arrive almost instantly, so they can serve as an early signal, a kind of advance notice that a supernova has occurred. This was demonstrated with SN 1987A, where neutrinos were detected before the visible light reached its peak. And as detection technology improves, scientists hope to observe more events in this way. Now, there is also the matter of gravitational waves. These are ripples in space-time itself, produced by massive, accelerating objects. In certain types of stellar collapse, especially those involving asymmetries or rapid rotation, gravitational waves can be generated. Detecting them from supernovae is challenging, but it is an area of active research. If successful, it would provide yet another way to study these events, offering information that cannot be obtained through light or particles alone. So the study of supernovae has become something broader than just looking at a bright object in the sky. It is a multi-messenger approach: light, particles, waves, each carrying different pieces of information, each contributing to a more complete understanding. And beyond the immediate observations, there is also the study of what remains: supernova remnants. These expanding clouds of gas and dust can be observed for thousands of years after the explosion. By studying their structure, their composition, and their motion, scientists can learn about the original event. They can trace how the shockwave moved, how the material was distributed, how the elements were mixed, and how the remnant interacts with the surrounding environment. So even long after the initial brightness has faded, the story continues. Now, all of this data does not just sit in isolation. It is compared, modelled, simulated. Scientists use computer models to recreate the conditions of a supernova, adjusting parameters to see how different factors affect the outcome. They test ideas, they refine their understanding, and over time the models become more accurate, more capable of explaining what we observe. But even with all of this, there are still questions, details that are not fully understood, processes that are difficult to model precisely. Because the conditions involved are so extreme and the interaction so complex, that capturing every aspect of the explosion is a challenge. So the study of supernovae is ongoing. Each new observation adds to the picture. Each new detection provides more data, and gradually the understanding improves. But it is never complete. There is always more to learn, and this ongoing effort reflects something broader about science itself. It is not just about having answers, it is about asking questions, about observing carefully, about building a picture piece by piece. And supernovae, with their combination of extreme physics and observable effects, provide a unique opportunity to do that. They are laboratories on a cosmic scale, places where conditions exist that cannot be recreated on Earth. And by studying them, scientists can test ideas about matter, energy, gravity, and the fundamental laws that govern the universe. So while the explosion itself is brief, the process of understanding it is much longer. It continues long after the light has faded, long after the shockwave has passed. If you take a step back from the details, from the collapse, the shockwaves, the different types and outcomes, something broader begins to come into view. Because a supernova is not just an event, it is a source of information, a way of learning about parts of the universe that we cannot reach directly, and in many cases a way of learning about things that would otherwise remain completely hidden. At first, it might not seem that way. It might seem like a supernova is simply the end of a star's life, a dramatic moment that produces light and then fades. But when scientists study these events carefully, they find that each one carries clues. Clues about how stars work, clues about how matter behaves under extreme conditions, clues about how the universe itself is structured and evolving. One of the most important things supernovae have taught us is that the universe is not static. This might sound obvious now, but it was not always the case. There was a time when people believed that the stars were fixed, unchanging, part of a permanent structure. But observations of supernovae, along with other discoveries, showed that change is a fundamental part of the cosmos. Stars are born, they live, they evolve, and they die. And in doing so, they reshape their surroundings. That idea that the universe is dynamic has become one of the foundations of modern astronomy. But supernovae go further than that. They also provide a way of measuring distances across the universe. This is where Type 1a supernovae become particularly important. Because their brightness is so consistent, they can be used as reference points. If you know how bright something truly is, and you measure how bright it appears, you can calculate how far away it is. This method has allowed scientists to measure distances to galaxies that are incredibly far away. And when those distances are combined with measurements of how fast those galaxies are moving away from us, something interesting emerges. The universe is expanding, not just moving, but stretching. Galaxies are getting farther apart over time, and supernovae have played a key role in confirming that, but the story does not stop there. Because when scientists looked at very distant Type 1 supernovae, they noticed something unexpected. Those supernovae appeared dimmer than expected, which meant they were farther away than they should have been if the expansion of the universe was slowing down. Instead, the data suggested that the expansion is accelerating. This was a surprising result, because gravity, acting on all the matter in the universe, would be expected to slow the expansion over time. But the observation showed the opposite. Something was causing the expansion to speed up, and this led to the idea of dark energy, a form of energy that permeates space and drives the acceleration of the universe. Now, dark energy is not something we fully understand. It remains one of the biggest open questions in physics, but the evidence for it comes, in part, from observations of supernovae. So in that sense, these stellar explosions have helped reveal something about the large-scale behaviour of the universe itself, something that affects everything, from galaxies to the structure of space-time. Now, beyond measuring distances and expansion, supernovae also provide insights into the behaviour of matter under extreme conditions. The core of a collapsing star reaches densities and temperatures that cannot be recreated in any laboratory on Earth. By studying the signals from these events, light, neutrinos, and potentially gravitational waves, scientists can test theories about how matter behaves in those environments. For example, the formation of neutron stars allows us to study matter at nuclear densities. The possible formation of black holes allows us to explore the limits of gravity, and the processes that create heavy elements allow us to understand nuclear reactions that go beyond standard fusion. So supernovae act as natural experiments that run on a scale far beyond anything we can build ourselves. And by observing them, we can gather data that informs our understanding of fundamental physics. There is also the matter of timing, because supernovae occur at different points in the history of the universe. By observing them at different distances, we are effectively looking back in time. Light from distant supernovae takes millions or billions of years to reach us. So when we observe those events, we're seeing them as they were in the past. This allows scientists to study how the properties of the universe have changed over time, how the rate of expansion has evolved, how the composition of galaxies has changed, and how the processes that drive stellar evolution may have differed in earlier epochs. So supernovae are not just snapshots, they are time markers. points in the past that we can observe and compare. Now, there is also something to be said about the role of supernovae in shaping the conditions for life. While this is more indirect, it is still significant. As we discussed earlier, supernovae produce and distribute heavy elements. Those elements are necessary for the formation of planets and for the chemistry that underlies life as we know it. So without supernovae, the universe would be a much simpler place, mostly hydrogen and helium, without the complexity needed for solid structures, for diverse chemistry, for the kinds of environments where life can develop. So in that sense, supernovae contribute to the conditions that make life possible, even if the events themselves are distant and in most cases harmless to us. Now, when you bring all of these ideas together, something becomes clear. A supernova is not just an isolated event. It is connected to many different aspects of the universe: stellar evolution, galactic structure, cosmic expansion, element formation, fundamental physics. Each explosion provides data. Each observation adds to our understanding. And over time, these individual events build up into a larger picture. A picture of a universe that is active, evolving, and interconnected. Now, of course, there are still many things we do not fully understand. The exact mechanisms of certain types of supernovae, the details of how shockwaves propagate, the precise behavior of matter at the highest densities, the nature of dark energy. These remain open questions, and supernovae continue to be a key part of the effort to answer them. So the study of these events is ongoing. Each new supernova that is observed provides another opportunity to learn, another set of data, another piece of the puzzle, and as our tools improve, as our observations become more detailed, our understanding continues to grow. But even with all of that, there is something else to notice, something that goes beyond the data and the measurements. Because when you look at a supernova, when you see that sudden burst of light in the sky, you're witnessing a process that connects the smallest scales, nuclear reactions inside a star, to the largest scales, the expansion of the universe. And that connection is part of what makes these events so significant. They bridge different areas of physics, they link different parts of the cosmos, and they remind us that the universe is not made up of isolated pieces, but of processes that interact and influence one another. Somewhere out there, far beyond what we can see with the naked eye, one of these events is happening right now. Not in a dramatic way that interrupts anything here, not in a way that changes the sky above you in this moment, but quietly, in the sense that distance softens everything. A star that spent millions of years holding itself together has reached its limit, collapsed inward, and begun releasing its energy outward. And the light from that moment has already started its journey. It's travelling through space, moving steadily, carrying with it the story of what happened. But it will take time to arrive, maybe thousands of years, maybe millions. By the time it reaches us, everything that caused it will already be long finished. And yet, when it does arrive, it will feel immediate. A new point of light, a sudden change in a sky that usually feels constant, something that wasn't there before, now quietly shining. That idea that what we see is not just distant but delayed has been part of this entire journey. Every stage we've followed, from the long life of a star to its collapse and explosion, unfolds over timescales that are difficult to grasp all at once. Millions of years of steady burning, a gradual shift in balance, a sudden collapse in less than a second, and then an outward explosion that can be seen across the galaxy. All of it connected, all of it part of a process that begins quietly and ends, at least from our perspective, with light. And that light is what reaches us. Not the collapse itself, not the moment when matter is compressed to its limits, not the exact instant when the shockwave forms, but the result. The energy making its way outward, crossing the distance between stars, eventually arriving here as something we can see, something we can observe, and something we can think about. Now, if you imagine looking up at the sky tonight, it probably looks familiar. The same patterns, the same steady points of light. Nothing obviously changing, and yet, within that stillness there is motion. Stars are forming, stars are evolving. Some are nearing the end of their lives, some are already in the final stages we've been talking about. But because everything happens on such large scales, both in distance and time, we don't see most of it directly. We see moments, snapshots, light arriving from different times and places. And when a supernova becomes visible, it stands out because it compresses so much change into something we can notice. A brief increase in brightness, a temporary presence, and then a fading back into the background. But even as the light fades, the process continues. The material that was ejected spreads out into space. It mixes with the surrounding gas and dust. It becomes part of the environment that will eventually give rise to new stars, new systems, new structures. So the ending of one star becomes part of the beginning of something else. Not immediately, not in a way that we can watch unfold step by step, but gradually over time. And this is something that repeats across the galaxy, across the universe. Stars forming, evolving, ending, and contributing to what comes next. It's not a cycle in the sense of something repeating exactly the same way each time, but there is a pattern to it, a flow from one state to another. Now, bringing this back to where we started, the idea of a star going supernova might have seemed dramatic at first, an explosion, a sudden end. But when you follow the full story, it becomes something more continuous, a long build-up, a brief intense transition, and then an outward spreading of material and energy. And within that process, there is no single moment that stands completely apart from the others. Each stage leads into the next. Each part is connected. Even the final explosion is not an isolated event, but the result of everything that came before, and the beginning of everything that comes after. So when you think about a supernova now, it doesn't have to feel like a sudden, chaotic event. It can feel like part of a longer story, one that unfolds slowly, quietly, and then briefly becomes visible before continuing in a different form. And as you sit there, maybe listening, maybe just letting your thoughts drift a little, it's worth remembering that the light we see from the stars is always a message from the past. Every point of light carries a story that has already happened. Every change we observe is something that unfolded long ago, and yet, when that light reaches us, it becomes part of the present, something we can notice, something we can think about, something we can quietly follow, even if only for a moment. So as things begin to settle again, as the sky returns to its usual calm, there is still that underlying motion, that ongoing process, stars continuing their lives, some nearing their ends, others just beginning. And somewhere, far away, another explosion has already begun its journey toward being seen, not yet visible, not yet part of our sky, but on its way. And in time, perhaps long after this moment has passed, that light will arrive too, joining all the others that quietly fill the night, carrying with it another story of a star that reached its limit, collapsed, and then, for a brief moment, shone brighter than almost anything else around it, before becoming part of something larger, something ongoing, something that never quite comes to a complete stop, even as everything within it changes.
If you enjoy exploring the universe in this calm and peaceful way, don't forget to like the video, subscribe to Quiet Science Nights, and leave a comment below so we can share and discuss together. This channel is created to bring you fascinating science stories, helping you learn while also relaxing after a long day. Thank you for listening, and I'll see you again on the next Quiet Science Night.